Buenas tardes.
Good afternoon and welcome to the Ramón Areces Foundation. On its behalf, I'd like to thank you for taking part in this event. My name is Manuel Aguilar. I'm a member of the Foundation's Scientific Board and an academic in the Royal Academy of Sciences. My specialty is high-energy experimental physics or elemental particle. No, the Areces Foundation has a very long established tradition in the promotion of projects and activities in the fields of science and technology. The Areces Foundation carries out these activities within a framework of cooperation with other institutions and foundations with similar interests, including the Royal Academy of Science, the Spanish Royal Society of Physics, Royal Society of Chemistry, Royal Society of Mathematics, the universities and research centres, as well as other foundations, both national and international. This evening's scientific session is a good example of these partnerships. It's a cooperation between the Areces Foundation and the Royal Academy of Science, the Institute of Mathematical Science of the CSIC, the Polytechnic University of Catalonia, the Centre of Mathematical Research, and the Autonomous and Complutense Universities of Madrid. And this scientific event is part of the Computational, Dynamical, and Geometrical Complexity in Fluid Dynamics project, which is funded by a 2021 program of the BBVA Foundation. The Foundation would like to thank everyone who's been involved in the organization of this event, and most particularly Professors Ángel González Prieto, Eva Miranda, Daniel Peralta Salas, and Juan Luis Vázquez, coordinators of this event, as well as our distinguished guests, Professor Yang-Hu He from the London Institute of Mathematical Science, who will be giving us a lecture on mathematical artificial intelligence, and Pilar Bayer Sanz from the University of Barcelona, and a member of the Royal Academy of Science, who will give us a lecture on the BSD conjecture, a mathematical enigma of millennial importance. The Areces Foundation would also like to thank all the researchers who are taking part in the second part of this event, the panel session. Before I give the floor to the coordinators of the event, I would like to refer to something which is unarguable, and that's the increasing current relevance of mathematics, not just as a scientific or technical tool, but also with a tremendous social impact. As a recent example, I would dare to quote a paragraph by Benjamin Calatu in his book Maniac, in an interview given to El País on October 28th, in which he spoke about why there's so much curiosity and interest in this fascinating discipline today. And he said, it's interesting, visible world which is not bound by any version of reality. The universe of mathematics is something that does not fit within the human mind. For me, he said, mathematics are the road that brings me closer to the mysteries which other people might divine through religion, mysticism, or shamanism. It's the realm of the invisible. Mathematics are something with which we can only interact through the use of our imagination and our minds, and it's therefore something that's really mysterious because its practical effects are all around us. And now I'd like to give the floor to Professor Juan Luis Vázquez, who is going to give you a few details about the event. And I'd like to thank all of them and our audience here today for partnering with the Areces Foundation. I hope that you will enjoy this lecture on this extremely fascinating and current topic. Thank you very much. Juan Luis.
Buenas tardes, queridos amigos.
Good evening, dear friends.
Yo les saludo.
I'd like to greet you. My role as a lecturer at the University of Madrid for many years. In fact, my first year at university was at the School of Mining Engineering in Oviedo because I intended to become an engineer. And then I started telecommunications engineering in Madrid, and I enjoyed it because it was full of mathematics, to the extent that I decided to become a mathematician back then in the 1970s, when everything seemed possible, and it was possible. I became a mathematician, and I presented my dissertation in the Complutense University. Then on January 1st, I went to the Autonomous University. I've worked in applied and pure mathematics since, and I'd like to thank all the institutions that have supported us in this challenge, listed there on the screen. I would, of course, like to start by thanking the Ramón Areces Foundation for hosting this event in this wonderful auditorium where they discuss all the advances and challenges faced by all the sciences regularly, both nationally and internationally. And then I'd also like to thank my institution, the Real Academia of Science, which was happy to support this event when we proposed it to them. And the BVA Foundation, which was at the beginning of all of this when the organizers showed the foundation the computational, dynamical, and geometrical complexity in fluid dynamics project, which they decided to sponsor in 2021. And the institutions around us and here in Spain have always been very welcoming and very supportive of this partnerships and cooperation. I'd like to mention CREA from Catalonia. I was in its committee for a while, and the CSIC in Madrid, which is the Center for Scientific Research here in Madrid, the Complutense University, the Autónoma University, which are the two universities where I studied. I'm currently an emeritus professor at the Autonomous University, the UPC in Barcelona, which I visit regularly. I have many friends there with whom we work in partial derivatives and some odd dynamical system here and there. It's a great pleasure, again, to be able to partner with all of them. And at my age, getting on, but still here. And of course, I also want to thank all the social institutions who support us, most particularly the Royal Society of Mathematics of Spain, the Spanish Society of Applied Mathematics, and GADEA, specifically today, which is also an institution that funds and supports science. I'd like to say a couple of words about important events that have taken place in Spain, where they have thought about the present and future of mathematics and the content of what we're doing. Specifically, in 2000, there was the World Year of Mathematics, which was an idea of the great French mathematician, Jean Prillos, and that was incredibly successful. We did not expect it. We couldn't believe that in Spain people realized that mathematics were useful, and yet people crawled out from under every stone to express their interests and their support. And that was really a turning point for our bond with Spanish society in general. In 2006, there was the World Congress of Mathematics in the wonderful facilities of the Madrid Conference Hall. And that was really, for me, one of the highlights of my whole life. And then in 2019, the Society of Applied Mathematics hosted the World Congress of Applied Mathematics in Valencia, which was also a huge success. And in 2020, the Mathematical Societies published the White Paper of Mathematics, which shows that there's tremendous interest in scientific research in mathematics in this country by specialized publications, but also by the general press. And you have to be not just clever from a technical point of view, but also intelligent in terms of disseminating what we do. And I'd like to finish by saying that mathematics are passed down to us. A building which 3,300 years ago already showed a crucial moment with the 13 books of Euclid's reflections in the Greek tradition. The Greeks had tremendous love for philosophy, and that contained mathematics, as the frontispiece of the Academy says. And if you read the Euclid Elements 2,300 years later, it's amazing to see how every line still makes just as much sense. There's been no destructuring of the elements. Because you can't, not because we don't want to. And in that sense, we have continued to make progress. And currently, mathematics have this great edifice which we all must maintain, and which is made up not just of the ancient wisdom, arithmetics, algebra, geometry, and mechanics, but also many, many others, the wonderful world of calculus, probability theory, statistics, and today things like data science. And I think we have a huge, brilliant task ahead of us to maintain that building, but also to maintain something else which we're going to talk about today, which is the love for the incredible power of thought, which opens new roads which people cannot perceive, and which will, however, change the world for everyone who comes after. We don't know how many years after, but it will. And so it's that impact of solving those problems which people cannot understand that we chase. Everything else is done by universities very well. And I'd like to thank you and welcome you once again to this event in which we want to hear a bit more about this shining breakthroughs of mathematics. And with that, I'm going to give the floor to Ella. Thank you.
Hola, buenas tardes.
Good afternoon, and thank you for joining us today while we explore the fascinating world of mathematics. Einstein defined pure mathematics as the poetry of logical ideas. But what do mathematicians say about their own discipline? Hardy, whom you know, since he was portrayed by Hollywood in the film, said a mathematician, like a painter or a poet, is a creator of patterns. And so Hardy invited us to think about mathematics as an art. But mathematics, are they pure or applied? Frankel, professor at Berkeley and also author of the well-known book Love and Math, answered half-jokingly that it's as if applied maths were my wife and pure math or basic math were my secret lover. And in that sense, I'd like to say that Kepler also spoke about the problem of packaging spheres because of a practical problem, which was how to pile up cannonballs on the deck of ships. And in 2002, the marine mathematics of Azovska, a Ukrainian, received the Fitch Medal because she was able to solve that enigma of how to pile spheres in a space with 8 dimensions in an A8 space. Space, which is part of the field of pure mathematics. In spite of that, we know that the solving of that problem has practical applications, for example, for data transmission. In the field of mathematics, there's still many mysteries to be solved, some of which are reflected in the list of millennial problems. What might be the impact of solving these mathematical challenges in our society? What will be the challenges for mathematics in the coming years, and how will they affect us as members of this society? Today we're going to talk about all of this together with well-known experts, and we've already you've heard that we're going to start with 2 talks, one by Yuhei from the London Institute of Mathematical Sciences and another by Pilar Bayer, in which we will once again talk about this dichotomy between pure and applied mathematics. Afterwards, we will have a panel session, which will be moderated by Arantxa Sanz, who's the executive director of the CRM, the Center of Mathematical Research. And so after this brief speech, I'm going to give the floor to my colleague, Daniel Peralta Salas, so he can introduce our first speaker. Daniel.
Buenas tardes a todos.
Good afternoon to everyone. I'm going to introduce you Professor Jiang-Wei He, who is the director of the London Institute of Mathematical Sciences and Merton College, University of Oxford. He has honorary positions such as the visiting professor at the City University of London and at the University of Nankai in China. And he is the chairman of the Scientific Global Society, which is called STEM. He's an expert in mathematical physics, string theory, algebraic theory, and numbers theory. And he works in the interface between all of these subjects and how AI and machine learning can help us tackle these problems from new points of view. Actually, he's going to lecture us about these issues. He's one of the pioneers in the world of AI for pure mathematics, especially interested in machine learning for detection of specular and string theory. He's been an author of more than 200 scientific publications, and he's a great communicator, as we will discover today, and he gives public lectures. Professor Huige, you have the floor.
Thank you very much for that kind introduction, and thank you very much. It's a great honor and pleasure to be here, and I'd like to first of all thank Eva and Angel for their kind invitation to this place, and thank you for your hospitality. I come from London, and I can boast for one thing, is that right now London is actually warmer than Madrid. So I'm going to talk about, I'm not an AI expert at all. I don't do machine learning. What I'm going to talk about is how I can use machine learning as a tool to help solve and raise problems in pure mathematics. So I think as the Professor Ayar and Professor Vázquez have alluded to in the beginning of the introduction, and Eva as well, what is mathematics? I think, in some sense, you can think of mathematics in three different ways. You can think of mathematics as what I call a bottom-up approach, namely mathematics as a formal logical system building up from the ground. You can think of mathematics as a top-down approach. That's what I call top-down, which is sort of as a creative and intuitive art. And you can think of mathematics as a meta-mathematics, as some kind of a language. And I'm going to tell you a little bit of how these three ways of looking at what mathematics is has been really revolutionized in the past 10 years by artificial intelligence. So before I begin with these three directions, I think it's undeniable that in the 20th century, mathematics has been absolutely using computers, to the point that I quote here, I think Kevin Buzzard, who says, there will be no more mathematics without computers, that we absolutely need computers and artificial intelligence to help us do this vast subject. Now, what do I mean by that? Well, of course, speeding up, I'm trying to get used to this. This is some artificial intelligence controlling this pointer. I'm trying to, there we go. So, of course, mathematics, computers speed up computations in mathematics. That goes without saying. But, believe it or not, if you're not a mathematician, you might be surprised that there's an increasing number of theorems in mathematics that the computer usage in which is indispensable. For example, foundational problems in mathematics. For example, the famous four-color theorem boiled down to a computer search at the end. I won't bore you with the details of these theorems. The famous Kepler conjecture of stacking balls, for which Marina Wierzowska won the Fields Medal last year in higher dimension, in dimension 8. The one in dimension 3, our dimension, was actually boiled down in 1998. It was solved as late as 1998 of a conjecture that was raised by Kepler in the 16th century using computers. The final check of his proof was by just exhaustive check. Furthermore, and this thing, very interestingly, the proof of the Kepler conjecture was accepted in 2017 by an automated computer theorem proving checker. And I'm going to explain to that in a minute what that means. It's perhaps even more shocking to people that the classification theorem of finite simple groups, this is one of the foundational problems in all of mathematics. It took almost 200 years to solve, and at the end of the day, there are 10 to 20,000 pages of this final proof of this theorem that not a single person has actually ever read. And nor is it possible to read, because it will take you longer than the human lifespan to study that subject and to read it. So the final checks of the various pieces of this classification theorem by many, many people like Gorenstein, many steps were just simply done by computers. So it's a natural thing to wonder, what is the future of mathematics? So let's start with bottom up. Okay, that's the first direction I was mentioning. Well, back in the 1910s, in the turn of the 20th century, Russell and Whitehead wrote a famous treatise, Principia Mathematica. Not the one by Newton, but this is a less famous Principia Mathematica, not Principia Mathematica Philosophia Naturalis of natural philosophy, but this is just the principle of mathematics. What did they try to do in this book was to try to raise a program of writing every single line of mathematics in formal logical symbols. Right? This is almost the definition of what bottom-up mathematics is. You write one sentence in symbols and then you build another sentence and another sentence. Of course, this really should go back to Frege and perhaps even to Leibniz, who thought about what is mathematics as a programming language. Leibniz, in some sense, invented the first computer. He was a contemporary of Newton. So these guys tried to axiomatize mathematics in this way, but Gödel in 1931, and almost at the same time, Church and Turing completely killed that program. Because Gödel showed his famous incompleteness theorem that there are statements in mathematics which simply cannot be proven within your framework of logic. And at around about the same time, Church and Turing showed their undecidable theorems, which means that there are sentences in mathematics which are undecidable. So you can think of this as a death blow to this bottom-up mathematics, the way that Principia Mathematica advocated. So it's always good to have two buts, because two buts cancel each other. I love this wonderful quote by my friend, Professor Min-Young Kim, who's a very distinguished number theorist. He says, "The practicing mathematician never worries about Gödel, because if we do, we'll be very, very depressed. If we have to start thinking about how many theorems that are undecidable, we'll just sit here and not do anything anymore." Sure, there are many, many statements in mathematics which is undecidable, but there are billions and trillions which are, so let's focus on these. And that's exactly the spirit that was taken by the so-called ATP program. So this is, ATP stands for Automated Theorem Proving. This is a long program that goes right back to 1956, which incidentally was around about the time that the first neural networks in artificial intelligence appeared. That was 1957. So people back in the 1950s were already thinking, is it possible to use what they then called a computing machine or logical machine to try to prove certain statements of Principia Mathematica from the bottom up? And they actually succeeded in some. Certainly not all of it. It's a very dense book, and I haven't read it, but I don't know, go watch the movie or something. But they proved certain subsets of Principia, which is wonderful. Back in 1956, before, when computers were the size of this room. So, and then there was there's a long history, which I'm not an expert in, called type theory, which tried to formulate a good machine language for formulating mathematics. So various people, Coquand, Martin, Loew, and all these people worked on this language. So Voevodsky, the Fields medalist, before he passed away, he was thinking, he was a homotopy theorist, but towards the end of his life, he was thinking almost exclusively on this problem. So I won't say very much about bottom-up because that's not what I'm actually using artificial intelligence for. But nevertheless, I think I should entice you about how we can use machine and artificial intelligence, and we have been using that even since as back as 1950. So there are programs now called, for example, there's the COC program, and then I'm still struggling with I'm machine learning how to do this, by the way. There's the COC system and there's the lean system, where there are automated theorem provers, and COC has now proved the four-color theorem in 2005, and the Phi-Thompson theorem in 2012. So this, if you're not a mathematician, don't worry. If you're a mathematician, these are very, very important theorems. Lean, the lean system, I have no idea what lean stands for, but it must stand for something very, very nice. Lean, as of 2013 to now, and just in the last few years ago, has all of undergraduate mathematics in machine code. Every single statement and every single proof of every single statement in undergraduate level mathematics. And they hit the run button, and they checked it, and it's good. Mathematics is consistent so far. Great. Now, of course, we still need graduate level and postgraduate level mathematics. People have to type all of this in, so somebody has to do it. So Davenport and Buzzard, in the two international congress meetings, this is where they award the Fields Medal, in two consecutive meetings, have talked about precisely this. This is the so-called computer-assisted proofs. And this is really, both people think that the future for mathematics is indispensably will be using systems like Lean. Of course, here's a very over-optimistic view from, surprise, surprise, Google DeepMind. This is Shagadi at DeepMind, because DeepMind just got involved in this in 2022. I'm going to involve just last year, and I will explain why DeepMind is interested in this. He says, well, computers beat humans at chess in the 90s. It beat humans in Go in 2018, and it probably beat humans at proving theorems in 2030. So this is a quote from DeepMind. And luckily, since Kevin Buzzard is a good friend of mine, and I asked him about it, he says, absolutely not. So mathematicians in the audience, you're still safe. We're still safe for a little longer, but not as soon as 2030. Maybe 2050, maybe 2070, I don't know. But the estimate by DeepMind is way too optimistic. We're not quite there yet. So that's it. That's all I'm going to say about bottom-up mathematics. Now let me just mention in passing about meta-mathematics, mathematics as a language. Of course, everything in the, it's in the public consciousness, large language models. Everybody's talking about it. You go walk on the street, everybody's talking about ChatGPT, right? So it's only a natural speculation whether there should be a ChatGPT for mathematics, right? So back a long time ago in 2018, my collaborators had thought about using some form of large language model. We did a very primitive thing of just downloading the archive, all of the titles of the archive. The archive for non-mathematicians, it's a repository where we put all of our papers. So in some sense, the archive is the most complete library of knowledge of mathematics since 1989. That's where it started. So we took out the titles and we did a large language model analysis. And within the titles, we found it has its own very interesting structure. So I won't bore you with the details. But one thing you can take home, and it's science, which is archive. And by the way, there's also a pseudoscience archive called VIXRA, which is archive spelled backwards. This is all of the papers that are rejected from the archive, including proof of the Riemann hypothesis. So every day there is one proof of one of the millennium problems on VIXRA, and it's just wrong. And things like Einstein is wrong, relativity is wrong, and it's an entire repository of pseudoscience. And if you do linguistic analysis of these two, you already tell they're completely different. They're separable. Good. So at least we should be assured that science is science and pseudoscience is pseudoscience. This is even from a linguistic point of view. That's a good check. So we were doing this back in 2018 before we knew much of anything. But then indeed, there is a Nature paper in 2019 by Chitoyan et al., where they did an abstract analysis of the entire field of material science. 3.3 million abstracts. So each abstract is about this much. Multiply that by 3.3 million. You have something like on the order of like 50 million words. And they did analysis of that. And they were able to use a large language model to discover new reactions, which then they tested in the laboratory and was actually better. So in that sense, the AI is performing better than the material scientist, very assuringly. But can you do this to math? We don't know, but we suspect that it might be, but it's going to be very, very difficult because math has too many symbols, and the structures of mathematics is more intricate than, say, material science. Because material science has a lot of the abstracts is about material A, material B, together will form material C. But mathematics has more intricate structure. Nevertheless, ChatGPT has passed the Turing test, which is great. I mean, this is quite amazing. We live in a very exciting times. Even 20 years ago, you would think, is it possible for robots to pass the Turing test? But now we are. I mean, people don't make a big deal about it. You have to Google to find, has ChatGPT passed the Turing test? But it has. We now have invented an artificial intelligence system that is indistinguishable from human speech and human understanding. So rumors have it that the OpenAI, all of the recent fiasco with the people resigning, non-resigning, Sam Altman, had fundamentally to do with their what's called Q-Star project. The OpenAI Q-Star project is exactly a large language model for mathematics. It should appear end of this year or early next year, and supposedly it should do mathematics based purely on the linguistics. We will see. Maybe that's our Christmas gift to ourselves. So finally, I'm going to actually tell you about what I'm going to tell you about, which is what I do, which is what I call top-down mathematics. Right? So I've talked about mathematics as you build from foundation up, and then you encounter problems like of Gödel. You can think about mathematics from an outside, as meta-mathematics as a language, but how do mathematicians actually do mathematics every day? What do we do all day? And that was Eva's question. We sit around. What do we do in our offices with blackboards? Well, we actually experiment. It's not a rude word. We love the word experiment. In some sense, mathematicians are experimentalists. We write our papers backwards. We doodle and say, this is wrong. We play, we try some numbers here and it doesn't work. And then when it doesn't work, we cover up all of the stuff that doesn't work and we write it backwards. Definition, lemma, theorem, proof. But it's completely written, but all of the details are hidden on in pieces of paper. But that doodling that we experiment with mathematics is where intuition and creativity is. Can we imitate that with artificial intelligence? And that's the key that I like to at least to say, yes, we can imitate it, but how far we can go with that. So there are countless examples of this in the history of mathematics. Calculus was invented way before formal analysis even existed. Algebraic geometry existed long before Bourbaki made it very, very formal. Galois theory existed before we even had a notion of what a group was. Right? Galois was just thinking about permutations. Right? So these things are just sort of a very hand-wavy, non-rigorous, intuitive understanding based on experience. So this is how are we going to do that? Right? So here's a question that I ask. What is the best neural network of the 19th century? Well, it's for sure the brain of Gauss. Forget about artificial neural networks. The best neural network that existed in the 19th century was this brain that was that was a natural neural network. At the age of 16, when people were playing football, Gauss looked at this graph. So this is a plot of the number of prime numbers less than or equal to a given real number x. This is what we call the prime counting function. Gauss just plotted it, okay? Imagine how hard this is, right? He had no computers, right? He actually had to compute by hand, primes up, or lookup tables up to primes in its millions by hand. And he plotted this, and he looked at this and said, so this is clearly x over log x. No idea why, because he had some intuition, maybe. Dirichlet and Legendre have some version of this, but I think Gauss just knew this because it was Gauss. But that's actually very interesting. In order to prove this, you had, 50 years had to pass before Adamard and Delavier-Poussin needed the technology of complex analysis to prove this. This was just something that came out of nowhere, right? That's interesting, just by pattern spotting, by experimentation of Gauss. Another fine example, which we'll hear shortly, is the BSD conjecture, which is one of the millennium problems. This is the Birch-Swinnerton-Dyer conjecture, which, interestingly, came from experimentation on a computer. Birch and Swinnerton-Dyer plotted ranks of curves and conductors of curves in a basement in the 1960s of a computer the size half of this room, and came up with one of the most fundamental problems in mathematics that we're going to hear shortly. And I'm really looking forward to listen to that. So this kind of experimentation is very standard to mathematics. Before you prove something, you can actually just raise some conjecture out of nowhere, of course, based on intuition and experience. So I'm going to give you some experiments. I think everybody can tell me what the next number is. You can shout out 0, right? Chances are it's 0, because I'm just giving you what is a multiple of 3. What about this? Okay, I'm not being very fair. I'm throwing something completely random. I'll be very impressed if somebody could guess it. Or at least tell me what this is. Okay, so I'm going to put you out of your misery. It's the sequence of odd numbers. It's a 1 if it's prime. It's 0 if it's not a prime. So this is the prime characteristic function. You can imagine if you stared at this long enough, you're probably able to spot it. What about this one? Okay, I'm going to quickly put you out of misery. We don't have that much time. This one's much harder. It looks completely random. So what this one is the parity of the number of prime factors up to multiplicity of the sequence of integers. This is sort of a shifted version of what's called the Liouville lambda function. Okay. So, number 1, very easy. Number 2, I think you can get it after about 20 minutes, if you like, whatever. The third one, if you can tell me what the next one is, Peter Sarnak is going to give you some money, because predicting that is equivalent to the Riemann hypothesis. There's an equivalent formulation of that in terms of the Riemann hypothesis. Again, one of the millennium problems. So it becomes natural to ask, is it true if I just fed these patterns into an artificial intelligence program, such as a support vector machine or a principal component analysis, the our familiar ones, it's going to struggle just as much as humans do? Well, everything goes back to Hardy. So let's quote what mathematics is. I love this quote. Well, I don't need to read it because it's so beautiful it's beyond words. Right? Well, what's relevant for us is that if there's one thing that an artificial intelligence algorithm can do better than humans, is pattern spotting. Probably the only thing. So can we pattern spot anything here that at least more or less matches what humans do? Or what mathematics does? So how do you do that? Well, let's uniformize this data. Okay, so I tried this. You can try something else. What you can do is to take, these are sequences of ones and zeros. I've made it very, very simple to be, as standard as possible. And then what you can do is to turn into what's known as a binary classification problem. Now, how do you do that? You have a sequence of ones and zeros. You take a window, and you take the first one outside of the window. So having seen the window, so that's your training data. You have a window of a binary vectors of ones and zeros. It predicts the next one should be 1 or 0. You keep on training, another one, train 1 million of these. At what point will one of these windows start to predict the next one with some confidence? Right? So this is a very standard thing you do in data science, but I think it's very well adapted to these problems in mathematics. Then you pass to your standard classifier. I mean, I won't bore you because I'm just throwing these words. I'm not an expert in machine learning, but at least I know some basic ones. You know, try your grandmother's kitchen sink algorithm, architecture, whatever you want. So I tried this, and you to say take 50,000 samples of these 3 data. Very quickly you find that any neural network will predict whether something is divisible by 3 within 100%. So what I'm recording here is the percentage of agreement to the 2 validation data. And this one is just sort of chi-squared, just for confidence. So, well, I mean, that's easy. Mod 3 is easy because, you know, it's a linear transformation that even a very simple neural network with 1 neuron can just detect it. The prime one gets 80% of them correct after a while. I don't know why it does that. I mean, it must be secretly doing some kind of SIF method. And the Liouville lambda function is great. It's 50% accuracy. In other words, it's guessing. It's as good as completely tossing a coin, right? 50% at 0.001 chi-square means that it's as good as tossing a coin. And, I mean, it doesn't say that your artificial intelligence is not solving these mathematics problems just as well as humans. It's just simply saying, at least I have not been able to find any neural network that breaks even for Liouville lambda. Of course, if I do find one, I crack the Riemann hypothesis, I get $1 million and you never see me again. Right? But I think that's going to be hard. So how did I actually get into this whole thing? Right? Because, you know, my background is in mathematical physics and in string theory. And I think that's from Ava's quote, that is my wife, and pure mathematics is my secret lover. So I'm a mathematical physicist by disguise, but it really just gives me an excuse to play with problems in number theory and algebraic geometry when in the dark. So my original motivation actually came from string theory. Now, I mean, this is not a talk about string theory, so I won't bore you with that. But what it is string theory is this 10-dimensional theory which unifies gravity with quantum mechanics. But it's in 10 dimensions. We don't live in 10 dimensions. We live in 4 dimensions, 3 of space and 1 of time. So the standard solution of string theory is to reduce 6 dimensions. There's these hidden 6 dimensions that we don't see. That's why algebraic geometry comes in, because you have to study 6-dimensional manifolds. The problem with 6-dimensional manifolds is that there are loads and loads and loads of them. Not just thousands, but there are as many as 10 to the 10 to the something, many of these, in different topological class. So I originally got into this problem in this paper I wrote back in 2017, which is, can I you can't calculate, not even by computer, you can't do it by hand, you can't even do with computer help in an exhaustive search for which is the right hidden geometry to choose for the real world. So I played around with trying to train a neural classifier to try to solve this problem. And it worked within certain context. I had no idea what it was doing. I still don't know what it was doing. All I know is that it was doing it to very high accuracy. So in some sense, a neural network was able to do very advanced algebraic geometry without any idea what algebraic geometry is, except the fact that it is just doing pattern spotting and pattern recognition. So in other words, a typical computation in algebraic geometry is to give you some matrix, and Bourbaki, who is the great French school of geometry, tells that there's some topological invariant. After sequence chasing, and you cry, you in the shower for many days, you get some number like 22. Right? But what you really should be thinking about is to take these as sort of an image processing, and then train this to millions of cases that we do know, and then check validation to see why it works. Okay. So, in other words, what I'm claiming is that algebraic geometry is, in some sense, an image processing problem. I've said this many times in front of algebraic geometers. I have not been shot so far. So nobody's killed me, so I think it's okay to say this. And there are some in the audience who are not shooting me. So this is kind of interesting. So I gave you examples of prime recognition, or division by 3, some simple problems in arithmetic. But even some problem as advanced as algebraic geometry or string theory compactifications, a neural network can very often guess right the answer almost all the time, better than us and faster. But there's a downside to that, is that we have no idea what it is doing. So how is that useful for mathematics? So then I started playing. So here I have a huge list of my collaborators. Since then, for the last 6 years, I don't spend any time with my wife. I spend my time with my lover, which is to go completely into, let's use the standard artificial intelligence algorithms to see every branch of mathematics, at least that I can understand, but with the help of many, many collaborators and friends. So, editing 2 books. Please buy these books. So I get the £5 per year royalties that we get from academic books. So what's kind of interesting is I'm actually running a conference this term in Cambridge. The title of the conference, this is jointly with many of my friends here. But the title is great. It's got everything, including your grandmother's kitchen sink in it. Black holes, number theory, holographic quantum information, and machine learning. Oh, sorry, it didn't even show, and machine learning, which is to bring experts from all these disciplines to try to see what are the current problems in mathematics that can crisscross. We were actually very honored that Birch was able to attend this conference and give a lecture on Zoom. I mean, he's 92 or something. But so we will hear more about Birch shortly. So Birch, together with Birch and Buzzard and Clem, we were able to formulate something which we jokingly called the Birch test. So ChatGPT has passed the Turing test, which is the test, if you blindfold yourself, are you talking to a person or are you talking to an AI system? So the Birch test is, it must be a mathematics conjecture generated by an AI system in the spirit that I was talking about before. It must be concrete enough to be a conjecture, right? Just because I have 99.99% solving some topological invariants in algebraic geometry, but I can't tell you what the neural network is doing. That's not useful either. And it must be non-trivial enough for a community of human mathematicians to work on it. Right? So Birch, of course, is a grandmaster, and he sets the bar very, very, very high. So let's see. ChatGPT certainly can't pass the Birch test yet, but what we're doing, this community, can it pass the Birch test? So here are some contenders. Oh, the most important thing is you've got to make Birch happy. He's 92, or 90, I think, 92. So here, just to finish up, so the candidates for the Birch test since 2017, by my collaborators, myself, as well as other groups. Well, the first one, I mentioned this learning of topological invariants in Calabi-Hodge numbers. I tried that. It was great. It's gotten up to 99.96% accuracy now in thousands of test cases. But it doesn't pass the Birch test because it's not interpretable. I'm giving you some neural network with 5 million parameters. It does it, but I don't know what it's actually doing. So it doesn't pass it. I tried in 2018 with Kim on separation of simple and non-simple groups. So just the one line, what that is they're in the space, I allude to this problem classification of simple groups. Simple groups are something like prime numbers. So if you can detect simple groups within the space of groups, it's like detecting primes within the space of integers. We plotted the Cayley tables of simple groups, and it's separated. So that's kind of interesting. So there's some natural, so we used, of course, a machine learning algorithm called support vector machine to do it. So this is a proto-conjecture. It's separating, but it's not precise enough to pass the Birch test because, okay, fine, it's almost there, but you're not telling us how it's separating and why it's separating. There's a very famous paper just last year this is the DeepMind collaboration. So this is why I mentioned DeepMind earlier. So Davies, Williamson, and DeepMind in a 10-author paper that appeared in Nature last year, which is they were able to take from a branch of mathematics known as knot theory, and they were able to generate a new relation amongst different knot invariants using a saliency test using neural networks. This also doesn't pass the Birch test. It is very precise, it is correct, it is generated by AI, but it's not non-trivial enough because they were able to prove this relation within a few months. Okay? So far, the only one that's almost made Birch happy is this one that we had with my number theory collaborators, Lee, Oliver, and Posniakov, where we use a human intervention in interpreting certain patterns in the distribution of L function coefficients, and we were able to raise a precise conjecture. I won't bore you with this conjecture, but this conjecture actually is very relevant to the BSD conjecture. And most importantly, it made Birch almost happy. The day that we make Birch completely happy, then we're on the verge of losing our jobs. So I'd like to end with this very prescient quote by Gödel about what mathematics is. I started off by saying mathematics. I try to approach mathematics in 3 different directions. And I think in all these 3 directions, the future for mathematics, and it's kind of nice that you have, 20th century, 19th century, the eyes of Gauss were good enough. The 20th century, you need computers in order to raise non-trivial conjectures. And the 21st century, inevitably, you will need some kind of artificial intelligence system for us to help us to do mathematics. So with that thought, thank you very much. Gotcha.
I'd like to ask you, what is your idea of the fact that pi is a Borel number with perfect randomness?
Yeah, that's a very good
Is this
question.
workable?
So I actually tried that. I tried training digits of pi in a 10-way classifier because we have unlimited data on that one. And I couldn't find anything that breaks 1/10 guess. So I'm not saying that there doesn't exist one. I just literally took 1,000 digits, tried to predict next one, another 1,000 digits, and then it came to like completely a 10-sided coin flip. So it's very difficult to see any patterns in pi because that's also a very, very difficult problem. Again, if one could find something, that would be very, very interesting. Thank you. That's a good question. Thank you very much.
He'll be back in a minute with an answer, be it yes, no, or we don't know. but he will be back.
Esperemos un momento a que venga Pilar.
Or actually, she will be back. It's going to be Pilar who has to come back.
Cuando yo les digo que hay 10 a las no sé cuántos cifras del número pi, dice, ¿han llegado al final?
Did they get to the end? Well, actually, the answer is there's no end because they're random questions.
Pilar, por favor.
Where's Pilar? She's disappeared.
Yo creo que no le sale, ¿eh? ¿Hay alguna observación sobre...
Do we have any remarks, maybe, about these issues proposed by Professor Hope? A round of applause for Pilar, who came back.
Bueno, para mí es un placer presentar.
It is such a pleasure for me to introduce you to Pilar Valle-Risant, who presently is a professor, an emeritus professor at the Barcelona University. She's focused on mathematics, which is normally known as arithmetic mathematics or number theory, which has made advancements in the knowledge of Z functions, diophantic equations, automorphic shapes, and arithmetic shapes or varieties. Throughout her background, she's directed 15 PhD theses, and led many research projects. Apart from her work as a researcher, she's played a key role as a professor in different Spanish universities, including the Barcelona University, the Autonomous University of Barcelona, the University of Cantabria, but also abroad in 2 German universities, which is Ratisbon University, which she worked from 1977 to 80, and in Göttingen University, which she was working in 2004. She's also an active academician in different institutions which are renowned in Spain, such as the Real Academia of Sciences of Spain, the Real Academy of Sciences and Arts of Barcelona, the Real Academy of Europe of PhD Doctors, and the Instituto de Estudios Catalans. At a more personal level, I need to thank her, actually, Pilar Valle. I'm here today, most probably, and I'm a mathematician today, thanks to the fact that she was my teacher, my professor. And she conveyed to me the passion for her work for mathematics. She contaminated this passion. So today, finally, we're going to be able to know what we mean by BSD. And we brought on a spoiler with the previous talk somehow. But Pilar is going to talk about the BSD conjecture, a very important millennial mathematical enigma. And this is one of the millennial conjectures, as Jean-P said. If you solve it, you will get $1 million. When the conjecture was proposed, $1 million would allow you to buy a big house. Not anymore nowadays. Anyway, you have the floor, Pilar. Thank you, Eva. I need to tell you that I remember you so well when you were my student, and it was a pleasure, and it is a pleasure to have you here. I'd like to thank the organizers of this event. I'd like to thank Ramón Areces Foundation and the Royal Academy and the rest of the institutions for giving me this opportunity to explain to you one part, an updated part of the mathematical research. It's a present one. Where's the pointer, the laser pointer I think she's looking for? I couldn't find it. Okay, thank you. Good. In 2000, the Clay Mathematics Institute, that calls itself an organization which is global, dedicated to promote beauty, power, and universality of mathematical thinking, formulated, advised by different scientists, 7 open problems. Next to each problem, I wrote down the year when this problem was formulated. And out of all of these open 7 problems up to now, only one has been closed, which is number 5. As you can see, these problems are or have a red dot. And that's what I'm going to maintain during my entire lecture. That is to say, what are open problems or conjectures will come with a red bullet point. And if it comes with a blue bullet point, that's because it is a theorem, so that I don't have to write down theorem. Okay? So this is number 5. It is solved in 2003 by Perelman. And the order of the problems is not what counts. I'm going to talk about the first bullet point, which is Birch and Swinnerton Dyer conjecture from the 60s, formulated in 1960. BSD conjecture. These are Birch and Swinnerton Dyer, 2 mathematicians from England. Swinnerton Dyer was from Cambridge, the same university as Hardy, and Birch came from Oxford. Look, on Birch's picture, you can see the term Adele. If I remember later, I will explain what Adeles are. The BSD problem has a very simple formulation. Up to now, it is open because it has a red bullet point, right? Wow. Okay, so this is the red bullet point, and the statement is as follows. For any elliptic curve defined over the rational numbers, its arithmetic range and its analytical range coincide. What are the mathematical concepts, therefore, that appear? Just 4. Rational numbers, we know what that is. Elliptic curve, arithmetic range, and analytical range. My intention during my talk is for you to live today by understanding this statement, by understanding what an elliptic curve is, what an arithmetic range is, and what an analytical range is. Some of you are mathematicians and you will say, is this what I came for? I already know about that, but some of you are not mathematicians. So my idea, obviously, is geared towards all of you understanding this statement. We will get formulas, obviously, which are addressed towards the mathematicians. And those of you who are not mathematicians, think like this is like a symphony when you listen, but you don't see the readings. And it's the musicians have it. I need to have it on front in order to know what I'm talking about. But look, but you need to understand that this is as if it is a music letter. So it's just about listening to music. This conjecture refers to arithmetics, and I'm going to talk to you slightly about the beginning of arithmetics. We're going to continue talking about number bodies, Z functions, and then we will understand the analytical range with symmetries, orthomotic functions, modularity to understand the conjecture quiz, and obviously initially in order to understand the arithmetic range, and we will end up by understanding the conjecture. Therefore, I need to talk about numbers. And by numbers, well, numbers have different natures. If you take a ruler, 1, 2, 3 are natural numbers. If you take a thermometer, you will have positive and negative, which are integers. And if you look at the middle one, those are rational, and integers are the other ones. And all of the numbers of the straight, you will give you the real numbers, and you will say, I cannot look at all of the numbers of the straight line. Well, I cannot understand all of the real numbers, because in order to write a real number, you need to write decimals, and it's never ending. The phi number that was included in the ad of the lecture, they took just one little piece. It's a rational number. It's not phi, really, or c, rather. Well, we need to talk about complex numbers because at a certain point in time, we need to talk about the square roots of negative numbers. Real numbers are all of the dots of the straight line, and complex are the dots of the plane. A complex straight line is a plane. We also need to differentiate between algebraic and transcendental. Algebraic are solutions of equations with rational coefficients. Rationals are fractions. And transcendental are those that you cannot see like this. It is very important to differentiate between algebraic and transcendental. Transcendence of C involves the possibility of squaring the circle. By the way, it is a theorem that can be explained in just 1 hour. Okay, this is the beginning of arithmetics. I'm going to set the origin at the same point where Professor Vázquez started. I'm going to start with Euclides elements. I'm going to continue with Diophantus from Alexandria, Fermat, Euler, and Gauss, which is the beginning of arithmetics. Euclides elements are a geometric books, but chapter number 5 is arithmetics, and Euclides shows there, proves that the set of prime numbers is non-finite. He doesn't use these terms because to Greek, infinite they didn't like. How does he state that? He says, no matter how many prime numbers that you write, you're never going to write them all. This is more or less a free translation of what he used to say, okay? And in Euclides elements also, there's a proposition which allows us to prove that all entire numbers break down in product of premium numbers in a singular number. That's important. It's not just that it breaks down, but it is that it is special, single, with the exception of signs, if I'm in set and order. This is called the fundamental theorem of arithmetics, that premium numbers are the building blocks in order to, or prime are key to build integers. Okay, we're going to continue with Diophantus. We go from the 3rd century before Christ to the 4th century after Christ, and we need to speed up because we need to get to nowadays. Diophantus Arithmetics is a book of problems. He says, I know, dear Dionysius, he says, student, that you like to solve problems. You have many numerical problems here. It is important because Greeks did not have a good numbering system. They calculated with an abacus, and you need to wait for the Arabs to have decimals developed, to have a zero, and therefore Diophantus proposed a question, and he found a solution, and then he's satisfied with it. He doesn't know whether there's more or less. He just found one. And problem number 4 says, breaking down 1 square into 2 squares, x equals z. And he says, let's say z equals 4, and he talks, and then he says, no, he doesn't say x and z. That's very modern. But anyway, 1 square, it's equal to 4, and the other one is going to be 16/5 and 5/16. Some people say that Diophantic equations look for equations in integers. Not really. Diophantin himself had rational numbers, equations, and obviously then there's denominators, which means that there is integers 16, 12, 20, or if I divide by zeta square, it means that 8/10 and 6/10 equal 1. That is to say, they give me 1 point of a circle, of a unit circle with coordinates which are rational. Diophantus is studied by Pierre de Fermat. Arithmetics was lost for many years. There were translations made into Arab, but in 1661 there was a new publishing by Bachet that has a version in Latin next to the Greek one, and next to the famous problem number 8, many of you know, Fermat said, this is the only case where a square cannot be the addition of 2 squares, nor a power which is larger, b square are 4 squares. It cannot be as the addition of 2 squares. So Diophantus arithmetics, it had a very narrow margin, and you all know that this margin was so small that Fermat couldn't prove the theorem. But there's an exception here, and we say Fermat's theorem, but actually Fermat didn't prove it, so it's a red bullet point, which is actually a conjecture, Fermat's conjecture. And then you say, she's going to talk about BSD, why is she not talking about Fermat? You will see, I know what I'm talking about. I mean every word I'm saying. I was talking about rational points of a circle, right? I know that the points of a circle unit I can describe with the sinus and cosinus functions, sinus and cosinus, that we studied in school that represent sound. We've all drew the graphs of sinus and cosinus graphs. On the left, you can see the real part, and on the right, it's a complex version. Functions, sinus and cosinus, it's periodical of 2p, which means that in the Euclidean plane, I'm doing lines, strips, and the functions repeat. They have this periodicity, which is Euclidean, given with translations of the module 2 phi. Thanks to this relationship discovered by Euler, I know that I can define the dots of the circle with values of sine and cosine. And therefore, when I detect rational points, I can think that these are values which are special of sine and cosine. And in general, sine and cosine, these values are described with the numbers which are equal to 1. There's many decimals, but sometimes they go through rational dots or points, and sometimes they go through algebraic points. So the first part is the stereographic projection, and this is a correspondence to each rational point of this line corresponds to a rational point of the circle. Actually, the Babylonic knew this before. And to the right, I have all the special values of sine and cosine functions, which are the roots of the unit. The vertices of irregular polygons inscribed in a unit circle. Why are they algebraic elements? Because they satisfy that x elevate to the n are equal to 1. They're special points. They're algebraic point that are expressed, some of them with roots and just with this value, some others. Why are they special? Because they're related to symmetric notions. The vertices of regular polygons give me special numbers. They don't give me transcendental numbers. They give me algebraic numbers. Good. Fermat studied Diophantus. Euler studied Fermat and Diophanto, and he looked for the properties of other numbers. Let's look for numbers, the square of which is equal to the elevated to 3 plus 1, which means finding rational special points of a curve, which is not really a circumference, but rather it is a cubic type of curve, this one here, quadratic curve. Therefore, Euler and Fermat, both inspired in Diophantus, developed what is called the method of the second tangent, which means that on this cubic, there's something special. In the same way that in a circle, we add angles, here points can be added. How do you add points? Well, the fastest way is saying 3 points add up to 0 if they're in a straight line. Once they found a solution, Euler and Fermat both, I have point P here, for instance, 2, 3, 2, 3. Why? Because 3 to the square is the same as 2 to the square plus 1. So they add twice P, and they have 3 times P, 4 times P, 3 times P. And then they did this to sine and cosine, and they went to the beginning, and sometimes they found solution, and they didn't come to the starting point sometimes. And then he said, I'm going crazy. I don't know when I'm going back to the beginning, and I don't know when I'm going back. So that's the thing. I may have a correlational point that moves, and sometimes I come back, sometimes I don't. Okay. BSD conjecture manages analytic tools, geometric tools, arithmetic tools. So I need to introduce different concepts, right? And I decided to do the following thing. The pages that refer to analysis are going to appear in blue. Those that refer to arithmetics, as we've been doing up to now, in light yellow. And then geometry are going to come in green. We still need some for algebra, but I'm not going to show them because algebra have to do with testing, with proving, with demonstrations. But I'm not going to show that. Okay, we have a blue page. What does that mean? This is the study made by Euler of prime numbers as Euclides deals with them. And Euler makes an alternative test or proving, which proves that there's infinite premium numbers, and he does it like that. And I'm going to do it in the following way. Once I heard to a professor that you need to do a proof in every mathematical exposure, I'm going to prove the divergence of the harmonic series. How does the harmonic series appear? By adding 1 plus 1/2 plus 1/3 plus 1/4 and so on. That is to say, by adding all of the relationships of frequencies generated by the harmonics of a sound. If you know harmonics, there are series of the harmonic series. I'm going to forget about the first two ones. 1/3 plus 1/4 is bigger than 1/4 plus 1/4, which is 1/2. Actually, these four here are larger than 1/8, 1/8, 1/8, 1/8. 4/8, 1/2. And little by little, I'm grouping them together, and this is the addition of the harmonic series, which is larger than 1/2 plus 1/2 and plus 1/2. It means that the series diverges, that the addition of all of the terms of the harmonic series is equal to infinite. But beware, because if these terms of the harmonic series I elevate to the square, then it does not add to infinite. Phi squared divided by 6, which is Mengele's result that can be proven in 1.5 hours of a lesson. Euler realizes that this infinite addition coincides with an infinite product at the same time. These are additions of geometric series of 1/3, 1/2, 1/4, which means 1 divided by 1 divided by reason. When I multiply all of these terms, and I realize that each one of these numbers are broken down as a single one, as a product of premium, and I then obtain the harmonic series, Euler realizes that the harmonic series that diverges is equal to this product of premiums, and that's extended to all these primes. And I may have a finite numbers, because a finite number would be equal to an infinite addition. And then Euler says there's infinite primes. Euler then considers a function of real variable, which consists on looking for values to the right of the one where the series converges, whatever it is equal to. It's a real number. When they talked about functions in Euler's times, they meant exponential, logarithms, and these were real functions. And then we started to call functions to anything: a law, a first set, a second association, any graph became a function. While here there's going to be many functions, and some of them are strong in character, such as the exponential, the log, and so on. Okay, let's go back to arithmetics. Gauss clearly proved that the integers are the product of primes, and Fermat observed that some were the result of square primes and some others, but he didn't know which was and which were not. And why is it that sometimes it is and why it is that sometimes it is not? In order to explain this phenomenon, Gauss increased the whole or integers by adding the imaginary unit. In this number, the red or the blue dots are the shape of the shape a plus I with a and b, which are integers. What are the red elements? Well, those are the prime numbers, but not z, but rather the new set that I'm shaping, which is zdi. Let's see the following thing now. A prime is a number that cannot be broken down into z. But when I add more elements, then maybe, yes, I can break it down. It's like particles which are elemental, if they're elemental or not. You increase energy, and there's things that were not breaking down, and they start breaking down. What is it that Gauss observes? Well, Gauss, I'm going to just keep the first quadrant because the rest are the same primes multiplied by I squared, and I squared, 3 squared. And I say the following thing. 2 is 1 plus 1 multiplied by 1 minus I, and 3 is prime. Here it stays in this line. 5 is 1 plus 2i. 7 and 11 are prime. 13, it breaks down. 17, it breaks down, and so on. The mystery then is that if a number stays prime, it does not break down in square numbers. And if it does break down, that means that it breaks down as the product of the prime elements of a larger ring. Z plus Ti, 2 plus Yn is a prime number. And Gauss proves, and that's in blue, that a premium number larger than 2 is a sum of two squares if and only if p equals 1. To understand something at the level of whole numbers, I need to go to algebraic elements to see what's happening. Okay, in Gauss's disquisitions, they studied the representations like this, and in order to study these equations, they're classified. How? According to the changes of coordinates, and these changes of coordinates are matrix 2 by 2 with whole coefficients A. So once they classified the equations, he realizes that in order to study them, it's good enough to study one type of equations, and it's important to know how many classes they have. Classes are equal to 1 only if these are the discriminants, 9 discriminants here, and in general, he needs to work with rings in this way, Z and so on, domains where it's addition, deduction, multiplication is good enough. And in general, when you add rational coefficients, also division. And you may study here whether the elements break down or not into prime products. And in general, he realizes that's not the case. And the lack of unicity of breaking down is measured by an amount, which is the number of classes. Okay, then now we go to the 19th century. Galois, Abel, Kummer studied Gauss. Dirichlet, the Kind also, with binary representations, Jacobi, Weierstrass, Riemann, they all studied Gauss and Euler and so on. And arithmetics then went one step ahead, a quantum step ahead, actually. Kummer worked by adding two whole numbers, not the imaginary unit, but rather the p for prime. The vertices of an irregular prime. And all of this element that is broken down in a single one in premium element products was Fermat's theorem. Dirichlet showed it to him, and he said, you know what? You're using an unicity of breaking down in premiums on primes on which I'm not so sure about. And then they need to study these sets and how far they are from being a domain of single factorization, how unicity fails. And that's true. Unicity fails, and these domains have a number of classes. If P does not divide to the number of classes, then Kummer's proof is valid. In 1850, they knew that Fermat's theorem was actually a theorem for all primes that did not divide to the number of classes, and these primes are called regular primes. And Kummer was very happy because he said, I've proven Fermat's theorem for infinite primes. Well, it's never been corroborated whether the set of irregular primes is infinite. Why the regular ones? It has been proven to be infinite.
But over an interval, the regular will always prevail over the irregular. But if P does not divide HP, then what Fermat said was true, and the first irregular prime where this demonstration fails is 37. And when I actually had my 37th birthday, I was scared. Okay, so if we continue with this Riemann zeta function, we've seen that Euler knew that the function was defined for all real numbers s greater than 1, and that at 1 it was asymptotic to infinite. And Riemann took up Euler's studies and formulated the so-called Riemann hypothesis, where every zero in the function is in the real part of this graph. But careful, because for the real part of s equals to a half, we didn't have any functions. And Riemann had to extend the function. That was brutal work. And what he did was the following. Of the zeta function, he provides this integer, which is the integer of another function with this exponential function, well, this exponent, and so on. And all that is interpreted as a function of a complex variable. And this for the real part of s greater than 1, so to the right of 1. But then the general can be transformed and applies to the whole of s. And so we've extended the function to the whole plane. And then you can see that this function is extended to the Heromorph function. And here, where it tends to infinity, there's a 1 in red, because we will have to return to this 1 later. And so he fine-tunes it a bit by adding what I call the infinite factor with the Euler and pi range, which satisfies this functional, very clear equation. And you know exactly that the point S for a half is in the center of symmetry. Oh, I'd lost my screen for a minute. Okay. So formulated the famous Riemann hypothesis, where all zeros have to be on the real part of this function, which is one of the millennial problems, but it's still not been proven. And the arithmetic, which Kuhner studied, said has to be extended to all integer domains. And I'm going to skip over this a bit quickly, but these completed as well as Q applied to periodic numbers for each ring P. We'll talk about this bodies later, but you have to introduce some techniques here. And so, for example, here we have a completion of Q, not with the usual absolute value, which would give you the real numbers, but with a 7 quadratic. So you change the distance in Q, you change the concept of elements that are closed and the successions of completed, and you get more numbers that completing the rational, not just the real numbers and the complex numbers, but you also have complete bodies for each prime number of P. And so the Riemann zeta function was extended to any plane of numbers as long as you add any element that is algebraic. And you do this in the following way. There's no unicity in the breakdown of the different elements. One by one, you have to pick sets, which are called ideal sets, and you formulate this function, which is similar to Riemann's Z. So the denominator is not n, it's the norm of an ideal number, which means that there's how many elements in the ring. And this breakdown has this Euler product plus a singularity in S equals 1. And this is where you get the next formula, which is this wonderful residue function. The function is by Dedekind, and this residue by Lilike, where it's 2 to the number of real roots, half the complex roots, pi to the half the complex roots, plus the regulator, which is the volume of the unit elements, plus h, which is the class number, plus the square root of the nominal, plus the number times the unit. And so with all of this, you then calculate Q. E equals R1 equals 1, ER2 equals 0, H equals 1, square root of D equals 1, omega or W or small WB, W is 2, and all of it gives you 1. Why? What does that mean? Applying Q to algebraic numbers. And I used to say to my students, well, the Z function of the number field is kind of like its DNA. There's a series of coefficients and numbers which tell us about the intrinsic structure of what these algebraic elements are. And for now, there had been no analytical prolongation, but Hecke achieved it a few years later, identifying these functions with others, which were associated to zero functions that are derived from manipulating the exponential function. All right, we should talk about elliptic curves. An algebraic curve in its simplest form, a flat model, is a two-variable equation with coefficients in a field K. And if it's complex numbers, then you might think about the real points in the curve or its complex points. And its complex points will be something of 2 dimensions, surface 2 dimensions. There's a theorem of classification for 2 dimensions where you just see this. Oriented surfaces, 2 dimensions, which include the sphere, which has a range of 0, the torus with a genus of 1 or 2 or 3, so it can be infinite. The complex points, once you've deformed them and put them through a topologist, will produce one of these forms. Elliptic curves, their complex points, well, in elliptic curves are derived from grade 3 polynomials, what Euler and Fermat were studying, as we saw. And so if we generalize, you obtain these curves in circumferences grade 2, and this one's grade 3, and then you parameterize. Instead of the arc-cosine functions, you can parameterize with functions Weierstrass or Jacobi functions. And these are, well, earlier we saw an elliptic curve with its complex points, like a torus, but you could think about real points, and so it would be an infinite line. And here, for example, you have a representation of the real points of this elliptic curve, or this other elliptic curve, and here there's 3 zeros, and here there's a single real zero. And these are part of the rotation of the complex points. And you could think about Fermat's curves, n equal to 1, for n equal to 2 it's a circumference, but then you get these curves for higher numbers, and you could think about what their range would be, which is provided by this equation, and then you have to ask, will they have rational points or won't they? This is Fermat's problem. And so complex points, for example, in Fermat curve with an exponent of 5, it's a 6-parameter curve, which looks very artistic in this picture. It's basically a surface with 6 holes. You can see this sometimes in physics projects, but what is the function that parameterizes elliptic curve? It's the p function by Weierstrass, and it's about getting a mesh and sticking one side to another, the top to the bottom. And, well, topologists say, but just cut and paste. No. And then you have to do the analysis, and you get a function with this kind of periods where the values coincide up here and down here, and you fold them and obtain a torus. And each torus has its own Weierstrass function. So the coefficients are part, the coefficients of the equation that's satisfied by p and its derivative are part of a mesh, which g of L and g of 2L, and each point has each torus will have its characteristics depending on the angle and the length and the vectors that are involved. But let's move to the 19th and 20th centuries. And all of these mathematicians, Riemann, Humer, Gauss, and so on, were their inspiration. But these are people like Klein, Poincaré, Hilbert, Hermann Weyl, Herke, Siegel, Hasse, Nether, Ramanujan, and Mordell. Oh, and Hiller, I don't know if I mentioned him, Hilbert. And they will all be working on problems which will lead to our goal. Right, we're going to have to move in general from the Euclidean plane to the hyperbolic plane, because there will be functions that are not Euclidean functions, but hyperbolic plane functions. As a model of the hyperbolic plane, you would have this upper plane with this distance, and this model of the hyperbolic plane can be related, once you know a little more, with a homogeneous space that is composed of this group of E plus a discrete group. You have to put it down like this in order to generalize. So elliptic modular functions, and it turns out that in a hyperbolic plane, like in an Euclidean plane, there are some groups, some symmetries, which apply. When mathematicians talk about the groups, physicists talk about symmetries. And their term is always better, because the term group doesn't tell you much, but the term symmetry is pretty descriptive, because in a hyperbolic plane, you have this modular group, which is a group of symmetries, and that's the group that Gauss used in order to classify binary quadratic forms. It's the same group. And so here you have this function which is linked to this structure, which corresponds the coefficient of the complex upper plane calculated by J with this group with the compound line. And this is function J, which is like the exponential function, but in this hyperbolic category, and it's called the J function of Klein. And so Klein says, and well, as Dedekind says, well, actually Klein's formula was Dedekind's, but anyway, here you go. And there are two basic fundamental lines, and you just need to know them for these values. These are the modules. These are the forms that are linked to the classification of binary quadratic forms, which give rise to this function. Okay, and so in the Euclidean finite plane, there's only 17 types of mosaic symmetries, but in the hyperbolic plane, there are infinite symmetries. And linked to symmetries of these figures, there are functions that are repeated following these models, and there are two different types. Triangles, with an angle in the infinite, and some triangles that do not tend to the infinite. And this creates a theory of functions which are modular functions. And here there's a theory of functions which are orthomorphous functions. The ones on the left were distinguished from the ones on the right because they have Fourier series, because when they tend to infinity, they have the translation and the others do not. They have developments based on parameters of local uniformity. And there are subgroups of the modular group which will give us actions on these mosaics and which will define a family of curves that Klein studied. Both Fricke and Klein studied these modular curves. As for the other side, the infinite triangles are the ones that Poincaré studied, which you may have heard called automorphous functions now, but he called them Fuchsian functions. And each of these automorphous functions has a genus, as a function of a complex variable, and there are these elements that are differential equations, which, like in Fourier series, we are talking about acoustics or sound. In this case, particularly in PS2, are vibrations. These are complex variable curves which have complex points and have vibrations, special vibrations, which we will look at from the arithmetical perspective. And so the genus of modular curves grows depending on the level. So in this case, when it's 2, it's a sphere with a genus of 1. X0 is a torus, X0, 22. There's these formula to obtain the form, but you might be interested in knowing the rational points of these curves. And in general, there are 3 situations. In genus of 0, there's either no rational points or they're infinite, as in a circumference. In genus 1, which are the elliptic curve, the set may be finite or infinite. And in a genus greater or equal to 2, it's always finite. And that's where the BDS conjecture comes in, because this set of rational points may or may not be finite. It's about knowing what happened to Euler when he went back to the beginning, or when he obtained solutions and solutions and solutions indefinitely. And so Poincaré in 1901, I'm going to use current terminology, he put it rather differently. He said the rational points in an elliptic curve with rational coefficients have this structure. There's an infinite part and a finite part. The infinite part, there's nothing to be said, but the infinite part, what's important, he says, is that it creates all points from a finite number of them. That is, there's a finite set of generators, and this finite set of generators was then called the range of the elliptic curve. And how many infinite order points do I have that are independent? And so the structure of the group of points was like this. That was demonstrated by Mordel in 1922. We saw his photograph. Poincaré's is still a conjecture. That's why it's in red. But Mordel's theorem said that Poincaré was right, and he proved that theorem. He just said, but this is the way it is. He's just clearly saw that it all had to come from a finite number. And so in the case of a genus of more than 2, it's a series of theorems that prove that there's only a finite number of rational points, which is a conjecture developed by Mordel, but we're not going to dwell on this. And torsion, the finite element points are not difficult. There are these theorems by Nagel and Lewis which tell you, given the equation, what are the torsion points, and people have been calculating them. But when they calculated them, some realized that they never exceeded 16 points of torsion and that 11 never appeared. But why does it never come out as 11? And why from 16 I don't get anything higher? And will this always be possible? And so with a lot of calculations, Levi, Nagel, and Ogg said, well, the torsion has this structure. You don't get 11, and the highest number of points is 16, a conjecture. And just like we saw that number fields have that zeta function, Hasse with Doide and Bell had the idea of connecting 2 elliptic curves, a zeta function, which is actually called the L function, but it has the same characteristics. It's the product of 1 divided by some numbers that extend to all prime numbers. And here you get a series which is similar to the one, Monica, but with these coefficients, A sub n, and A sub p is greater or equal to 2, times the square root of t. So this is a series that converges in a semi-plane for the real part of s equal or greater to 3/2. 3/2. And so they left it there with its properties greater than 3/2. And Hassel said, well, it's like the Slay series, which will extend to the whole plane. But then Hasse developed this conjecture where the L function, appropriately fine-tuned with these gamma factors, will satisfy a functional equation and will be defined for all complex S's. But this is just a conjecture. And in fact, it's defined for the real part of S greater than 3/2. And so then Doirin realized that Hasse was right because of some very special curves, which are the curves with an extra symmetry, which is complex multiplication, which extended to the whole plane. So there were these elliptic curves where you had a function of L available for the whole plane. And then we move into the 20th century, and here comes Shimura, so Tanyama and Bell up here, these three, and Eichler and Levin-Grothenberg, who revolutionized the language of algebraic geometry. Payne, who worked with periodic, I'm not going to go into that, but that was pretty crucial. And Searle, we'll see when he comes in and also plays a crucial role. There was a conference in Tokyo Nikko in 1955, and a student, Kaniyama, presented the following. He asked to find out whether the elliptic curves defined on a number field can be parameterized using automorphous functions. And people said, what? What? Elliptic curves can be parameterized with the Weierstrass P function, which comes from a mesh in the Euclidean plane. And these automorphous functions are the ones defined by Klein and Poincaré from the hyperbolic plane. So what is he talking about? And so Shimura realized that elliptic curves parameterized with modular functions did satisfy Hasse's conjecture. What does that mean? That certain elliptic curves have an L function that can be written as an integral of a real function of those that come from the modular field and could apply to the whole plane. And so Weil looked at where to find these functions, and these were linked to the modular curves that Klein had studied. And they came up with this conjecture, STW, Shimura, Taniyama, Weil. All elliptic curves E over Q are modulars. They all have to come from the hyperbolic plane. Apart from the Weierstrass ones, there have to be some hyperbolic functions that will provide these parameters. Equivalent forms, an elliptic curve defined over Q, if you shine a lamp behind a modular curve and project it on a plane, or when its coordinates are described with functions in JJN, or their L function extends to the complex plane and satisfies a specific modular equation. Its L function gives us coefficients which provide the vibrations of a modular curve linked to this level, which you calculate based on the coefficients of the function. So this is a conjecture. It was a conjecture, and then gradually from the 70s, a lot of numerical evidence was gathered to show that it could perhaps be demonstrated. And also, Harry Maser proved that torsion had this structure that had been predicted by these calculations, of course. And in the demonstration of Maser's theorem is a whole PhD dissertation by several people, but it's linked to the behavior of modular curves. An in-depth study of modular curves proves that the torsion of elliptic curves over Q is a maximum of 16. And that was exactly the structure that had been predicted back in the day. And now we can come to the last part of the talk, which is actually the BSD conjecture. And here you have Maser, who's just done that in-depth study of modular curve, and these guys at a wedding, and the first results with Faltinch, who had looked at those curves of as greater than 2. And then the big surprise here, and here's Wiles, who proves Fermat's theorem. Why a surprise? Well, you'll see, but there was a time when BSD was connected to Fermat's theorem, and torsion had been settled and understood, and so Birch, Bryan, and Swinnerton-Dyer started to think about how to calculate the range, that is, the number of independent points. One thing is to look in depth at the elliptic curve and look at the z function of the elliptic curve, because that's where you must find information about the range. And so let's look in point 1 and see what happens. And then the order of 0 in point 1 should be the range. Except that when Birch and Swinnerton-Dyer decided to do this, the function had been prolonged, and people said, well, that's an interesting conjecture. Range, when you don't have algorithms to calculate it and we don't know what it's going to be, it's equal to the value of 0 in a function where the function is not defined. So it was great. And so here you have them having t and looking at the number of rational points in the elliptic curve in this donut. And this is the graph from the functions defined just for the real part of this curve, greater than 3/2. But the information has to be found in this red dot of s equals 1. And so what are they thinking? Let's imagine that we've removed the torsion, which is a finite number. So they're thinking about how many almonds have been used to decorate this donut. If you cut them up into chunks, then you can calculate all the multiples of these numbers, what the number of almonds is in the DNA, which is the L function, but it hadn't been defined at that time. And so this is the conjecture as it appears in the millennial problem, but they go a lot further and they say the main part is equal to 0 with all these characteristics of the elliptic curve, which I'm not going to go into. And so what they do is, with a computer that had recently arrived at Cambridge, which filled the whole room with perforated cards, for the elliptic curves with complex multiplication, where you could prolong the L function, they gradually gather numerical evidence that this conjecture might be true. And so they worked on it and worked on it, and there's been a lot of work done on it. In 1977, there was an initial result in this dissertation by Wiles, led by Coates in Cambridge, saying that if 0 is a simple number, of course, if 0 is simple, then the order is 0, which means there are no infinite order points. The range of the elliptic curve is therefore 0. Demonstrated by Coates and Wiles using these methods. And then Gross and Sager, in an amazing piece of work in 1986, which would take another one whole year seminar, produced this formula of the derivative of the L function of the elliptic curve over the quadratic of the height of a point. If L is simple, then this order is 1, and this derivative is different from 0, and this point cannot be a torsion point because torsion points have a finite height, and so the range has to be greater or equal to 1. And since this height comes into the formula of the derivative, you have at least one almond. You have at least one point of infinite order. And then in 1990, Kolviagin says if the order is 1, the range is infinite. And then there's all this finite parameters for the algorithms, but that's where they left it. And then people were all excited because it looked as if that conjecture was proving to be true. But then suddenly Frey realized the following. Reading Hurwitz and Gillois, he realized that if the Fermat equation had a single solution, you'd be able to derive an elliptic curve over Q which would not be modular, where you would not be able to prolong the L function. And so, of course, that was a shock because it meant that if the Shimura-Tanyama conjecture was true, if the L function could be prolonged, it could be used not just to justify the T conjecture, but also Fermat's theorem, if Frey was right. And so Frey asked Shane and said, is this true that this curve could not be modular? And Sir said, well, yeah, if you look at this, then this detail, then yes, of course, the epsilon conjecture demonstrated by Ribet, and that was in 1986 all the way to 1990. These were 4 amazing years. And so what happened was that to prove the STW conjecture, that is, to do the analytical prolongation of the Z function of elliptic curves by chance. It's like when you go to the supermarket and you buy 2 products and get 3 for 2. You demonstrate Fermat's theorem. That's what happens. If you do the analytic prolongation, then Fermat was right. And there are solutions. And here, for example, there's a lot of calculations. There's a whole database, the Cremona database, which is amazing. This is one point. This is a grade 1 curve. But look at the rational point, what it looks like with these coefficients, which are not that unusual. So to do these calculations is actually very time-consuming. We can have a very small rational point with a numerator and a denominator that would both be huge. So the calculation work here is tremendous. And here there's checks that the SDG conjecture is true. And then when they realized that the PDS conjecture implied or involved the Fermat theorem in 1990 is when Weiss locked himself up in his attic. Everyone's heard this. He heard something and just locked himself in the attic. And 5 years later, he came down. And yes, he had managed to demonstrate that the L function is in an elliptic curve is an integral transform of the function that is connected with those modular curves, so a vibration of that modular curve. So Weiss actually just solved Fermat by the wayside, because really what he proved was that the L function of an elliptic curve is modular, is prolonged, and then you have the Fermat theorem right there. So we have the Fermat theorem right there, and with the Wiles theorem, that conjecture, BSD conjecture, makes sense, because they're saying the range is equal to the order of the 0 in S equals 1. But S equals 1, now I know what that means. It's defined, and it can be calculated with these integrals and so on. And so all of that is integrated, and I've explained it for elliptic curves, but actually this has been going up to higher dimensions and elliptic curves with a billion variants. With an elliptic curve has a billion variant of dimension 1, but there are these objects which are motivic worlds, which are geometrical objects that have an L function. That's what they are. And then from here you move to the L functions from the geometry in the Grotin sense, motivic theory, to the L functions, and these L functions, since we start from geometry, are defined in planes or regions, and I need to prolong them in any dimension. For an elliptic curve, it was all this. Where do you have to go? Well, you have to go to the equivalent in a higher dimension, which are the modular curves, which have quotients with discrete groups, and so that's the automorphic world, where there are great symmetries which allow you to extend all the functions you like or that come from the motivic world. And yeah, that has to be demonstrated. And how do you demonstrate that? By generalizing the Wiles demonstrations and Serre's ideas, which is by deformation of Galois representations. That is, if the elliptic curve was modular, then it would transmit the modular character up, and you get to point 0 where things no longer vibrate. So this whole Galois theory is used for the demonstrations. And algebra basically comes into all the demonstrations. And that's the end, except for this small detail. Just like the professor named his students, I also enjoy mentioning where I learned all these things. And that's been by working with different seminars and groups that Eva mentioned, and that's how I've selected these 10 articles of people who are currently working in European projects, who've gone to the US and Finland and France and Zurich, and they're all working really hard because there's a lot of work to be done to understand these demonstrations, to simplify them, and to pass them to higher dimensions. And around these things, we have the following Able Awards. In 2003, Jean-Pierre Serre for his involvement in the Fermat demonstration, John Tate for all the local parts, Pierre Deline for the theory of motives and the conjectures, Andrew Wiles for the demonstration of the Shimura-Tamaraye conjecture for elliptic curves, and Robert Langlands, who's the one who says about where all of this has to be integrated or can be integrated in order to achieve a more global view of mathematics. So the thing is, you can have different geometrical objects, different analytical objects, but these special points, these special curves, why do they exist? And all of this is studied in abelian spaces where there are real complex numbers. And sometimes I think, well, these abelian spaces are probably dark matter. And all these L-periodic functions that I'm studying are probably all about dark energy. Maybe someday that could be an interpretation. But anyway, here is a European project for Shimura varieties, which is for a couple of years with €1.5 million. This is funding, so not awards, so that people can do some research on these things. And finally, here we have the two of them going home, BSD, very happy, going home. And by the way, I should say where I've used artificial intelligence in this presentation. I've used it in 2 slides. Everything else was human intelligence. For this DAL-E, for the drawings were produced by an AI. Thank you.
Muchas gracias, Pilar, por poner música y las partituras. No solo has hablado.
Thank you for adding music and mathematics. You've talked about 2 conjectures, Riemann's conjecture and Byzantine and BSD, Byzantine-Dyer's conjectures. Thank you for all of the details. Let's see if there's some questions on the audience. Let's see who asks, who dares ask. Someone from the youth. We have a question somewhere, right? Thank you, Pilar. I enjoyed a lot, as always. I have a question. Do we have a generation of the BSD conjecture for bodies, which is not Q? Does it have to be Q square? Oh, no. People are working on how to generalize the conjecture, BSD conjecture, for number bodies. Bodies of number. This has been formulated, the BSD. But Shimura-Taniyama-Weil conjecture, that's another issue, but it's being worked on. So they need to come from functions related to Shimura's varieties. That's why Shimura's manifolds appear. The Shimura's manifolds are shaped, the SL2B matrix 2 by 2 with the whole coefficients that are invertible, but that's part of matrices with whole coefficients that are one part of the ring with rational coefficients, and the rational coefficient matrices are an example of simple algebra. So it's being worked on algebra, on rational, on bodies of simple numbers, the quaternion, the most simple ones. They generate varieties from here, and from here onwards, you're going to have a whole set of functions in order to generalize Shimura-Taniyama-Weil, in order to generalize BSD. But all of this is under study, and obviously it's so wide that some people are working in different directions. And then afterwards, what I said, that in order to have the functional equation, you need to tune the L function in order to know what factors in the infinite you need to set. For that, you use Hodge's theory, according to Set's conjecture, because everything needs to be related. If you do not complete well the factors which are finite with infinite factors, you cannot guarantee the functional equation, and you're going to lose the symmetric axis, which is going to give you the information. And then obviously the following thing happens in an higher dimension. You have L functions for each one of the homology and adelic DDL. I have an L function here because I'm in dimension 1, but I have different L functions, representations of Galois, and everything is going up and up and up. But it's a lot of work because you need to do calculations when you may do them, and theory. Obviously, it's more, it's deeper and deeper, but they're working on it. Now, a definition where everybody agrees, to be honest, I think we don't have it yet. That's why in the Millennium Problem, they were so cautious. They just talked about the equality of the rank with the order of 0, not even the main part, and certainly not in higher dimension. Thank you. A round of applause.
Me he quedado con las ganas de preguntar.
You know what? I wanted to ask you about AI in these conjectures, but we're going to hold a round table that we're going to start right now. And please, I'd like to ask the panelists to come up to the panel. And I'm going to give the floor to Professor Peralta Sada.
Vale, pues sin mayor dilación.
Without further ado, I'm going to introduce the participants of our panel, even if we do not have a round table. But anyway, Pilar Bayer, in alphabetic order, you heard that she's a professor of the University of Barcelona and that she's an academic of RARC. She's an expert in number theory. Verónica Bolán, who is from the University of A Coruña. She's an expert in AI. Diego Córdoba, who is a professor of research at the ICMAT, expert in equations and partial derivatives and fluid dynamics. Ruiz Abella, professor from the Barcelona University. She's an expert in analysis and complex dynamics. She's been awarded the Real Academia 2020. Ángel González Prieto, who is a professor, assistant professor at the Madrid University. He's a professor in automatic learning, machine learning, and he was awarded the Vicente Casellas 2021. David Pérez García, professor of the Complutense University of Madrid, a member of the MAT also, expert in analysis and quantum theory, an award, Ramón y Cajal of RAC. And Juan Luis Vázquez, an emeritus professor at the Madrid Autonomous University, and he's an expert in equations and partial derivatives, and he has been awardee also of the Research Pastor in 2003. And up to now, he's the only one, and for a long, long time. The chairperson is going to be Arantxa Saz, who is the executive manager and the person in charge of strategy of the Impact Core Group. Thank you, Daniel. I'd like to start by thanking the coordinators of this event and the organizers, actually, Daniel, Eva, Juan Luis, Ángel. Thank you for inviting me to chair this panel. And obviously, I'd like to thank Areces Foundation and the rest of entities that thought that they should support meeting, the title of which is not often discussed, Challenges in Mathematics. And we will talk about what we mean by challenges later. Social impact is also a very important term and part of this panel. We use the term challenge here to provide some mystery. It's like things that are still pending solutions in mathematics. According to mathematicians, who says what is a challenge for mathematicians? And the impact social part, we're going to use the term impact with different meanings throughout this panel. So there's going to be an impact for the mathematic community, and we're going to talk about different sectorials, not only about this analysis, but also there's a media impact. When we discussed the title, I was told, yes, that's what we mean. As Daniel said, I'm in charge of coordinating the impact strategy that we research centers have to deal with nowadays. In a very, very long term, what is our science going to be used for? That's what we mean. And we want to see whether the media impact represents the future social impact. Does it? If it does not, is it just a hype subject, as it happens often in sciences? So we need to talk about whether the challenge is going to have a big impact or not, and who decides, and so on. But in order to open the debate, I'm going to ask you in alphabetic order. Veronica is going to give us a slightly different perspective. So will you please tell us what you mean by challenge in your different fields of expertise? Why is it that each one of you believes that it is still a challenge or an open issue, or where does this come from? Is it a part of a list, or is it posed by the community? And what would the solution involve? Would it have a media impact, an impact on economy, or other in sciences? Pilar, you start, please. With my due respect, you know what, I'm going to give the floor to the next one because I've been here speaking for 1 hour. I don't know. I gave an example, one example of one of the problems, but there's so many others. Anyway, I will just say something. Hardy, everybody quotes him, worked on the numbers theory. And seeing the way things were doing at the end of the Second World War, he said, I'm very happy that I've never done anything useful. Well, nowadays, I do not think that he would be very happy because we're in front of digital technologies, and digital technologies based on transforming information into numbers. And the numbers theory includes codes that correct errors and go into cybersecurity issue. Just to give you two examples, the first example is an error or a back error code. When we see that when we went from vinyls to CDs, Red Solomon codes, we correct the errors, the bugs, the mistakes. So everything that the knowledge of numbers has represented in order to deal with this information, in order to try to improve that. Now, what is it that we're doing now? Maybe in 100 years or in 200 or maybe in 20 years, we do not know, will be eventually applied. But digital technologies have been such a revolution that a field of mathematics that could be used just to have fun, if they could have fun, now instead it's useful, unexpectedly useful. And I'll leave it there. Maybe later I can explain other things. Can you hear me? My research line is framed within the mathematical analysis of equation in partial derivatives, and my specialty are those equations that come from the fluid dynamics. Depending on the context, these equations may be parabolic, hyperbolic, but above all, they're equations which are nonlinear and non-local. And the mother of these equations, so to say, are the equations of Euler and Navier-Stokes equations. Euler wrote the equations of, or rather the movement of a fluid that is not understandable nor homogeneous without considering the forces and the frictions between or among molecules, viscosity, but he described them in 1775. And 70 years later, in 1820, in 1850, actually, Navier and Stokes independently wrote the equations that explain the movement of an understandable and homogeneous fluid by considering the friction amongst molecules, that is to say, viscosity. And these equations were written more than 250 years ago. But in 1920, finally, it was proven that these equations have solutions. By solutions, I mean that we provide an initial piece of information. We say how the fluid is at t time equals 0, and we want to know whether these equations gave you a result, a solution for times which are larger than 0. That was done in 1920 by Helderich, Tels, Delahaye, Euler, and Navier-Stokes. And years later, once we know that there are solutions, the question was whether these solutions exist for all time. And 2 or 4 years later, Wallinger and Leray proved that in dimension 2, these equations exist for all time. But in dimension 3, it failed. The same estimates, the same calculations did not work. So this has become a problem, one of the problems of the millennium. Knowing specifically when the millennium problem was written down, it only considered the problem with viscosity, Navier-Stokes problem. And well, the list of problems was written down in 2000, and as Pilar explained, only one of them has been solved. But I would say, and that's the feeling that the fluid experts have, is that the next problem that is going to be solved in the next 5 years most probably is going to be the problem of Navier-Stokes. Why? Because computers play a very important role. And now, with computer-assisted proofs or proving, 2 years ago it was proven that in the case of a fluid in a domain which is limited, the singularities which happen in the borders. And this year, the first result that was a computer-assisted proving was done with initial data, which were regular, but maybe not so regular. And this year, in the archives, they filed a paper, I don't know how long, maybe 200 pages long, that uses computer with computer-assisted proving in order to prove that you can consider finite solutions, which is really the millennium problem. That's for Euler equations without considering viscosity. And at the same time, 2 years ago, Tarek El-Hinden, a young guy, proved the first result of singularity existence within, not in the borders, but within the fluid, and that is one of the millennium problems. But once again, in his case, it is for low regularity and without viscosity. And these results are 270 years after Euler's and Navier-Stokes writing the equations. Now, I need to tell you, my personal contribution is that this year, in the ILCEMAT group, we've proven 2 more results of singularity existence for Euler's equation. And we're very proud of that. And those are scenarios which are absolutely different to the scenarios of Tarek El-Hindi and of those of the group of the computer-assisted proving, which are Tom, Ho, and Ten from Talca University. To answer your question, Arantxa, about the involvement that would have, what that would represent, well, getting to know or not whether there is singularities is really not going to give us anything else apart from knowledge. But behind these proofs, there's being methods, strategies, new mathematics that are coming out that can help us solve all the problems, understand better the formation of singularities in fluid dynamics that may explain how tornadoes are formed, how they evolve, or how cold air and warm air fronts are shaped, or how a drop of water, when you open the tap and it gets a critical volume, then you close the tap and the drop doesn't stop there. Rather, there's a bottle neck that is formed and it drops. That's a singularity. Well, those type of problems could be solved after trying to solve the millennium problem. Apart from that, now talking about the importance of the Spanish contribution to this race to solve the millennial problem, there's another group led by an Spaniard, a young guy from Vallecas, Javier Gómez Serrano, who did his PhD thesis with us in the ICEMAT, and he's now a professor at Brown University, and he's an expert in computer-assisted proving or proofs. And they are working on the millennial problem with neural networks, with AI, with machine learning. They've published papers on El País, in Quanta magazine, and they've published a paper on physical review letters, and they're competing against Caltech Group by Tom Ho.
Y bueno,
Okay, and so the fact that in order to prove the millennium problem, you need to use all this technology, which to me is still science fiction, I think could be a good contribution. Hello? Can you hear me? We could. Now she switched it off. It was working. Yes, you can hear me. Okay. Yes, we can. Go ahead. What is she doing? Just talk.
Es que está parpadeando. A ver, ¿cuántos voy a romper? No aprietes ya. No aprieto. Vale, ya está. Lo siento. Bueno, buenas tardes.
Okay, good evening. My area of research are dynamic systems. Dynamic systems, to put it simply, well, life is a dynamic system with lots of variables. And in fact, in this field, we study models of real situations with techniques that are not just about solving, but qualitative techniques to analyze asymptotic behaviors and the phenomena we're studying. So the solar system, for instance, would be a dynamic system, and there's so many other things, life in general, as I said. And so then we model, and then we also study the models. That's the more theoretical part of it, perhaps. And on the more applied side of it, there's millions of challenges, as you can imagine, with great breakthroughs in technology, with things like we saw in the pandemic, the importance of mathematical models in general, unsolvable, but how with the use of computers and with the theory of dynamic systems, you can make predictions about the future based on models of the past. And in its more theoretical side, we try and study classes of dynamic systems and to come up with solid theories that will allow us to apply them to concrete cases. And I would say that on this more theoretical side of things, which is where I work, one of the biggest challenges is, just to mention one, which has been around since the 80s when the Stevens-Mail list was published. This was a mathematician from Berkeley who published his own list of challenges in this field. And to date, most of these are still unsolved. And one of them was the question, are hyperbolic systems generic? And here I have to explain what it means, but just very briefly, a hyperbolic system is a system we all understand very well because it's a robust system. It's a system where all solutions eventually will converge towards a situation of equilibrium. You could think, for example, about a population model where some species coexist with others in an ecosystem which is not broken, and so over cycles, these species ebb and rise, but stably. So if you alter it, there are no dramatic changes or consequences. But one of the questions asks, are all systems in certain classes? Of course, this question only makes sense when you're thinking about real dimension 1, complex dimension 2. So how many variables am I studying? And so one of the questions is, are all hyperbolic systems that I might randomly choose within this class be approached with these robust systems? One possible answer, of course, this is just a very rough way of describing this question, but essentially that's the question, which I would compare with asking, do all functions with certain characteristics, can they be approached with polynomials? Why do we care about this? Because if we can approach things we don't know with things we do know, then we can use these knowledge and gradually push it to the limit and learn about chaotic systems or systems that are difficult to understand. And so this is actually a crucial question. If a class of systems, if the answer is yes, then it means that if you pick a system at random, even if it entails some difficulties or chaotic behaviors, by altering it slightly, I will be able to get into the system of equilibria, which I know and understand. And so this question, which may seem very innocent, is something that it has taken years to solve in just some cases. In real one dimension, for example, in sufficiently good models, I'm not going to go into the details, it's been proven that this is true and that, yes, all systems or hyperbolic systems are dense. But, for example, in complex dimension 1, which is where I work, we don't know yet. And that is one of the big central challenges for complex dynamic systems. In dimension 2, it's been proven to be false, etc., etc. So this question, which may have seemed, in principle, pretty innocent, is still an open question. And I would say that it would have a big impact if it was solved, not just because of what it would imply in applications, but also because this is a question that's connected with the topology and the theory of numbers theory. And like all big questions, it does have connections with many other areas, and so it would have consequences even at the graphic level because it's connected with the famous fractal of the Mandelbrot set. I'll leave it there. Well, thank you very much. I don't actually need a microphone. My voice is that loud. But just to mention a challenge which I think is pretty crucial in geometry, and we of course, want to understand spaces that are defined by mathematical problems, but also sometimes by problems in physics or in IT or in biology. And these spaces technically have a very high dimension, they cannot be drawn, and they have a very complex geometry. These are very intricate spaces. And as I work in geometry, I'm really bad at visualizing and painting things. And so what solutions do we find from geometry to understand these spaces, to associate? We connect invariants. We connect certain algebraic quantities to characterize a property of these spaces. So, for example, Professor Bayer was speaking about the genus of a surface, the number of holes. And so in this way, with these invariants, we try and understand whether these spaces are complicated or not so complicated. But there's a question which is sort of backwards, and that is, if you give me these invariants, can I build a space that will have those invariants? That is, if all these algebraic quantities, which tend to be numbers or polynomials, can be done. And this is a problem that's present for all of geometry. The Poincaré conjecture, which is the only millennium problem that has been solved yet, was a question about producing these invariants. And the other problem with the millennium list, which is still open, is Hodge's conjecture, which is a more sophisticated formulation of something similar. Why would we worry about this? Well, first, because it would give us a much deeper understanding of spaces. And as I said, these spaces are imported from other problems. These are borrowed problems, and therefore, if we shed light on these borrowed problems, it can help us improve our physical interpretation or understand certain biological systems or even climate systems which we don't understand right now. And this is not just a mathematical exercise, but also about the applicability that having these proofs would give us for other problems. Hello, I'm David Pérez García. I work in quantum computation or quantum computing, and instead of talking about a challenge, I'd like to talk about what might be a good choice of a challenge for mathematics, which also I think fits within this discussion. And we've heard about a lot of lists, and mathematicians have always loved making lists of problems, and that's all very well, and it has a lot of advantages because these are problems that take time and for which it's been found that since they're very non-trivial, solving them requires combining different areas of mathematics, as Pilar has explained so wonderfully in her talk, even with those different colors in the slides. And that's great because I think you have to build bridges, but of course it also has the disadvantage that these are problems that have been around for a while, and therefore they may also ignore the emergence of new problems, which are also very interesting and which mathematicians should be paying attention to, which may be connected to artificial intelligence, we've heard, or quantum computing, which is where I work. Quantum computing is an idea which has been around for a long time, but it's only recently exploded. In fact, 2 or 3 weeks ago, there was a big conference here on quantum technology in Europe. And the fact is that big corporates like IBM, Google, and so on are investing a lot to create increasingly powerful devices. And I'm sure you've read it in the media that IBM recently announced a new generation of quantum computers. And so I think mathematicians perhaps have the duty of also getting into these new fields and seeing whether there are some new interesting problems to solve there. And specifically, quantum computing, probably the biggest challenge is understanding or proving how much better a quantum computer is than a traditional one. There are some interesting algorithms that a quantum computer can produce, which a traditional computer cannot, or it would take a long time to produce, let's say. And so in mathematics, the way of formalizing is difficult. It's a problem in the theory of complexity, and so in a certain class of complexity, which are the problems that a quantum computer can solve efficiently, which is as how you compare that with the complexity classes of traditional computers, those that it can solve or verify efficiently. And that's the problem of P versus NP, which is in the list of the millennium problems and the classical side of things. But it's interesting, and in fact, there's been some new classical algorithms that have emerged from a certain quantum range, which we've seen can be turned into classical algorithms. These are called quantum-inspired algorithms. And to what extent is it true, therefore, that quantum computing is better than traditional computing? How much better is it? Because that would help a lot to create new traditional algorithms or new quantum algorithms, or at least to understand how necessary this investment is to create these quantum computers. Yes, good evening. As most of these panelists are going to talk about the big mathematical challenges that remain, which require a lot of depth and which are part of the heart of mathematics. I, since I was once an engineer, would like to look at it from a more global perspective, from the perspective of all the sciences. Mathematics has provided other sciences with concepts which enabled us to work with numbers and forms and geometries. And even in the old days, they tried to understand the mechanics with mathematics. And that was always very useful because it gave the concepts they created, as Plato realized very easily that mathematicians were creating virtual worlds with very deep concepts. And they provided three characteristics. One, that they were very clear. Two, they were very easy to distinguish from one another. And third, that they were very precise. And so this idea of being clear and easily distinguishable is extremely important today, where so many of the ideas of ancient philosophy, which are still around in our societies, of course, are subject to a constant deconstruction, and where we end up not knowing what we're talking about. In math, we do tend to know what we're talking about, and the concepts that are different from one another are easy to distinguish from one another. Really, one of the great applications of modern computational techniques is about separating things that are different. And on the other hand, precision is a crucial element of mathematics, where computers are able to do works with incredible precision, but they cannot do them without the mathematical apparatus behind them and underneath. I'm an expert in partial derivatives, and so I know that the computers we use every day in order to experiment and to validate our calculations, theory is based on differential equations supported by functional calculus, essentially Newton and Leibniz and everyone else's heritage. So there's something I'd like to say from a different perspective, and that is that mathematicians as a community, we must look carefully at our weaknesses, but also understand what our strengths are and what our challenges are. And I think the basic weakness for maths today is what is called the curse of complexity. We have too many things on our table. There's too many concepts. There's too many figures. There's too many relations. There's really difficult to manage it. In our own specialty of partial nonlinear derivatives, students, in order to be minimally ready for a dissertation, need to go through about a dozen PhD courses, each on a different topic. And we really need to deal with that because it makes things extremely difficult. And of all the basic characteristics of mathematics in Euclid's day, which was geometry, arithmetic, and of course, to some extent, mechanics, and also soon after, algebra, we've now added, since development of calculus, all kinds of additional fields, mechanics of continuous media, particles, mechanics, then electromagnetism, and then statistical mechanics, and then in the 20th century, a beautiful mathematical theory, which is relativity, which has transformed our concept of space, which was what was certain at the beginning. But also with quantum mechanics, we've seen a change in our concept of vacuum. Currently, a quantum vacuum is not a vacuum. And so, on the other hand, the 21st century does pose the challenge of integrating all of this, and we're pretty ready to integrate completely new things like quantum computing and data science, artificial intelligence. And I'm really happy because all of these things are being approached here with this spirit with mathematicians always demonstrate, which is a sort of desperate optimism, which is very admirable. And what could be the problem here? Well, not being able to do all these things all at once. And we might just be tempted to patch certain fronts and not ever go to enough depth in any. And so I think as a response to that, Spain's making a reasonable effort to make sure high-level groups focus on problems that could either be very profound for the human spirit and therefore intrinsically very beautiful, or very relevant for applied science, or extremely visionary for potential things that could happen in the future. And so I think that in that sense, the situation is quite promising, but what worries me, and that's one of the big weaknesses of mathematics right now, is that the clarity with which mathematical objects are perceived, distinguished, and computed is not present in society right now. There's a complete confusion in terms of the human mind's ability to grasp clear, precise, and determinable concepts of daily life. And mathematicians should be making every effort to disseminate the beauty of the certainty of science. Thank you.
Hi, good afternoon. As we've said, I'm the outsider, so to say. I'm a computer engineer. I'm not a mathematician, and I've worked for several years in research of AI. If you ask me what's the challenge of my area presently, it is difficult. Nowadays, AI is the elephant in the room everywhere. And there's many challenges because it has a big social impact nowadays. So it is like a big responsibility, a big power. There's many challenges. But to me, one of the challenges that I'd like to focus on right now is that we need algorithms of AI to be more efficient. It is true that we're being able to advance impressively, but these advancements have a computational cost, many hours, many weeks, months, during which these algorithms are learning what we call the training phase. For instance, the ChatGPT, the well-known ChatGPT, the free-of-charge model 3.5, there's an estimate that says that one single session of training, and there's many, consumes so much energy as 126 households in Denmark in 1 year. Well, it's Danish because they did it at the Copenhagen University. And this is just one training session. There's many others. And then there's the consumption every time we use it. So the time we're living right now, in my view, is such that we want to have spectacular advancements and developments with AI at no matter what cost, because these large companies may afford the financial costs, having many machines and so on. But as a society, we should demand more efficient algorithms. And this is where I believe we may get the help of or the assistance of mathematics. I am going to start by assuming that there's a clear synergy between AI and mathematics. We may say that the calculator is the precursor of a computer, so to say. And within this synergy, for instance, DeepMind is a company that has an algorithm that is called Alpha Tensor that with AI has been capable of finding new algorithms to multiply the matrices, matricial multiplication. That's interesting for mathematics, but at the same time, that's interesting for AI because there's many of the algorithms we use that do lots of multiplication of matrix type of operations. So it may help, or new algorithms of optimization and so on. Therefore, I always see AI as a very interdisciplinary subject matter. Those of us who work in AI cannot just stay within our own field. Rather, we need to always talk to other areas. Obviously, mathematics is one of the most important ones. At the same time, I believe that AI can help us solve challenges which are important in mathematics, such as one of the speakers said, that most probably at some point in time, AI is going to solve some of the millennium problems. Because we have the classical AI, which is machine learning, that starts with labeled data. We start with existing knowledge. But Alpha Tensor or AlphaFold or AlphaBow, which are the ones that win in chess games and go and so on, is a strengthening learning. Data are not labeled. We may go beyond the limits of knowledge. There's a lot of simulations required, but that does not mean that we cannot achieve unbelievable advancements or developments. That's it. Oh, I'd like to thank all of you for giving us a very wide point of view of different challenges and some specific questions. I have a comment for Veronica. May I make the remark? It's a short one. I agree with you, Veronica, when you say that AI, as we've said, is an aid that we've got, and it has positive and negative things, and it's here to stay. But there's something that we worry about from the point of view of inheritance of mathematics, which is that mathematics have been able to put a logic order into all of the disciplines that mathematics have touched. And these algorithms of neural networks that learn by experience, which is repeated, we don't know what they do. And somehow we get nervous as citizens in the world. What is the hope that you have about that? Or what's your expectations with that respect? Well, there's two big branches of AI, which is symbolic AI, that was popular up to now. It was more regular, rigorous, more logical, more mathematics. And now we have the sub-symbolic or connexionists, which are neural networks. And there's no mathematical rigor there. There's many, many operations that we do not understand. I would love for these algorithms of neural networks to be explainable, so to say, so that we understand what it does. That's one of the big challenges of AI. But presently, we're still not there, but we know that it works really well. So when they tell you there's two planes, one, we know exactly the way it works, but sometimes it falls. The other one, we don't know how it does, and it flies, but if it's been tested a lot and it always flies, it never falls. Which one are you going to go on? I know which one I'm going to jump on. You choose. In an ideal world, I wish these AI algorithms to be explainable, rigorous, mathematically, and so on, but for the time being, they're not. And that is another challenge that we need to face. Well, thank you very much to all of you. Most probably, that was one of the questions that many of the people in the audience was thinking about, the relationship between AI and mathematic efficiency and rationality. We've learned a lot today. And we've learned that many mathematical challenges of deep mathematics, of the future of mathematics, in order to understand its full rigor, such as BSD conjecture, are included in these problem lists. The millennial one is the most popular one, the one that has appeared on the media most. And there's others, such as the ones that have been mentioned by some of the panelists here. But really, why is it that these challenges are allocated to some fields or not? Or why is it that they represent this deep mathematics? Or how come they make mathematics develop? It's not just a contest, right? Could you, David, please elaborate more in detail? What are these challenges useful for? Obviously, the rest can also say something. For those of us who are not mathematicians, such as me, who am a physicist, it's easier for us to understand the problems which are the visionary part, as Juan Luis said. We physicists love partial derivatives, which is his specialty. But anyway, why is it that these problem lists help mathematics advance? How does it need to work so that they are really useful? My idea is that challenges and problems are developed when it is a deep problem and the solution of which requires new connections in different fields of mathematics and new ideas and so on. So when we advance, we just analyze things more and more in depth. Obviously, we look for twin solutions and so on, as Langmans does. But there's other problems where maybe there's been developments, there's others that where we have not evolved so much and they require new theories. Where there's been development, well, more or less we see the solution, but in other problems maybe we don't. Such as P versus MP is one of those problems where we don't even know where we need to head. But anyway, I think that it's interesting to focus on the problems, the resolution of which require the development of new theories so that mathematics per se advance, and there's other unexpected applications eventually, such as what Pilar said about Harvey's contributions. Maybe the applications can be even more interesting than what one wanted to solve initially. As I said earlier, it is important not to think that it is an interesting problem just because it's included in a list, because it needs to be open to new problems that may emerge and so on. This is a situation at the beginning of the 21st century, which is similar to what happened at the beginning of the 20th century, when suddenly there were two not easy to understand phenomena, which were relativity and quantum mechanics. From the experimental point of view, physicians saw that those phenomena, which were strange, existed and had to be understood, and they didn't know how. And well, there was a big effort for 20 years in both cases by physicians and mathematicians, thanks to which we were able to get wonderful equations which are called Einstein's equations of general relativity and Schrödinger's of quantum mechanics. Mathematics grew spectacularly. There's full departments of universities dedicated to that. There's thousands of children all over the world that are studying quantum mechanics and relativity and then became professors and lived happily ever after. But on the other hand, with mechanics that had been done based on mathematics, Dirac, one of the big prodigy boys in 1931, discovered a new particle, positron. And that was truly talking about the fact that mathematics provided a clarity of thought that allowed someone to do a prediction that had no experiment. The experiment was done by Yukawa and Hedemeyer, but a little bit later. So I do believe that with respect to the chaos where we're living still, with the complexity, huge complexity that we're seeing, and with AI, we need a big effort, a combined effort, so that in 20 years we may say that we do understand already. Mathematics are able, if they're supported on engineering and physics, we can understand a lot of the world that opens ahead of us, in front of us. I do believe, with respect to the question about why is it that we mathematics like lists, well, there's an essential thing which is related to the nature of our discipline. A physicist goes to a lab with some electrodes, magnetic fields, something happens, and he says, I do not understand. I have a problem that I need to study. While a biologist sets some bacteria to culture, I do not understand. I have a problem. So I study. While a mathematician, the nature of mathematics is more formal, is more ethereal, and that is such that you need problems to guide you, as in all disciplines. That is why lists are important. But as David said, it is very important not to just focus on the fact that the only important problems are the problems of the millennium. It is not true that there's so many research groups as millennium problems and that it is the only thing that is researched in mathematics. Certainly not. I think mathematicians research and understand phenomena and problems, and occasionally, tangentially, maybe you say, oh, my research work is focused on this problem or on this other problem. Actually, Professor Valle explained that very clearly. Andrew Wiles, when we tested the last of the maths theorems, actually he was not proving that theorem, but a different one. It is important. Yes, we need to use it in order to guide ourselves, but not with a limiting vision that this is the only thing we need to do. Going back to what I said at the beginning, that when we organized the panel, we were discussing what we meant by social impact and what it is that we mean by media impact, whether social impact, which are eventually the changes that Juan Luis was referring to, or some things that we're going to try to recover from some of the millennial challenges. It's sort of like a mathematics fun thing for privileged minds, but eventually it has unexpected consequences for the life of everyone eventually. So the mediatic or the media impact sometimes is equivalent to social economic impact of change potential of 100 years later, but not always, right? What we, not mathematicians, see is that sometimes Poincaré's conjecture or similar times when there's a genial person, type of Hollywood type of character, are the main characters of mathematics, and sometimes they are not known by the general media, right? So the media impact of mathematics in this case, is it the same as change potential, or are we really not really being told like that?
A ver, desafortunadamente.
Unfortunately, I think the fact that a mathematical discovery is covered or not by the media does not necessarily correlate with its importance. I guess, I don't know what the reasons are, but perhaps one of them could be the mathematical knowledge of journalists, or lack thereof. Why is something covered in a newspaper? Well, perhaps because it has an obvious practical application. That could be the reason, but most mathematical discoveries, especially the deepest, don't have an immediate application. So you can't sell it as if this is something that's going to fix all our problems next week. And so in these cases, why is an important deep theorem covered by the media or not? And the reasons, again, are often not correlated with its importance. It could be maybe because there are some very spectacular looking images, or the Millennium Problems apply because there's that $1 million reward, or because they've been on a list for a long time. But you rarely come across in the media something that really is conveyed in a language that people can understand. There's not enough knowledge of mathematics to understand the beauty in itself of a deep result. So I think there's room for improvement here, of course, with better education, like everything else, with more awareness of the fact that mathematics are not just a tool at the service of immediate gain, but that often is a long-term investment for the future, for something which may, in the future, be solved. Okay, I'd just like to mention two aspects. Over the years, I have realized that sometimes when people ask you, and what's this for? And you think hard and about how to move from mathematics to the real world and so on, what they're actually asking is, can you make money with this? So then mathematicians feel very far removed from that. What I mean is that we're not really very good at explaining what we're doing is for. Even if there's the assumption that there might be a big corporate who might use your algorithms, the minute they're in the hands of the company, mathematicians keep working in their universities and their research centers testing theorems. So really very far removed from those practical day-to-day applications. And that's why we give the feeling when people talk to mathematicians, they get the feeling that we don't actually know what it's for, because we're not really aware of the economic benefits, because the theorems or the mathematical results are not being, I forget the term they use. What's it called, that word? Monetized? What? The products? Yes? I think she means monetized, but she can't think of the word. That's right. Yeah, and not patented. Yes, exactly. Mathematical theorems are not patented. And so you can't say, well, with this theorem, my center has obtained this many millions in revenues. And so what it's for is not always very apparent. And that's one thing. But the other is that mathematicians have a crucial role, which is to educate all the teachers who will be teaching our students to have an organized brain. And that was something we rarely say. Sometimes a former student said, I looked through your CV and there's not a single course you've taught on that. And it's true. It's all about papers here and there, but not about I taught this course or that course. And I do spend a lot of hours training people and educating people. And right now, I think that El País newspaper says that our students are not doing well in mathematics according to the PISA benchmark. And yet, we don't value it. It's really difficult for mathematics to be valued in their raison d'être because it's about the human mind's ability that can be developed to its fullest and which has a lot of inherent value. And it's not so much about you selecting a problem because it has such a price or an award connected to it. It's the problem that chooses you. You, based on your interests, create some skills and abilities, and then you see an open problem which you could attack. And who could resist that? No one. We're not working on problems to get the $1 million, not at all. And so you just specialize, and then gradually, together, we cover this field, which maybe 25 years from now could be applied in technologies which we have nothing to do with, which will benefit the whole of society. Could we aim for something better? I sometimes get the feeling that we are like small neurons in a brain, but we're all connected, and together we get that brain moving. Of course, all technology progress has two sides. It can be used for good or evil. And so mathematicians perhaps stand aside, and what I think is that we need a society that is educated so that it's aware and knows to assess which is the right way to go and which part of mathematics should be applied in which directions and which parts should be left to one side because they will make things worse and not better. But that's how I see it after all these years in the field, thinking about it. And when people ask me what the use of what I do is, I never go far enough. People never quite get it. It's just the way it is. Well, I'd like to say that Spain has changed a lot in the last 20 years. And what you're saying is true, that one of the questions we always get asked is, what are mathematics for, and what's the use of mathematics? But I never get asked that question. 20 years ago, I got it all the time. But I think in these 20 years, society in Spain, in general, have realized that mathematics are a crucial pillar of the progress of technology. When you use your phone, your GPS, that's all mathematics. When you listen to the news and you look at the weather forecast, I think people in Spain do realize that there's all this mathematical work underneath. And when I started studying, the average grade to get into university and study mathematics was a 5. And now it's one of the highest grades to get in. And so that's a huge change. And my friends and relatives now tell me, oh, in my company, they're hiring mathematicians. And it's true, they are. And mathematics are now much in demand and have a tremendous impact on daily lives and businesses. And that's why I'm so proud to live in this country. And I think our society has made a lot of progress, and we just have to keep working and moving in that direction. I'm sorry, no microphone. Yes, I just wanted to jump in here because there's something we need to discuss. I think maybe I'm more on Diego's side right now. Some parts of mathematics, because of course it's like music, there are different genres and styles, and some parts have more contact with society and with applied world than others. Through my friends, I have experienced in Spain the evolution of applied mathematics to signaling theory, which is crucial, together with numerical calculus today, for everything to do with media. Portaselles unfortunately passed away. He was a very close friend of mine. He lived in Barcelona. And the idea was that the combination of Fourier analysis and numerical techniques completely changed the way in which applied mathematics was used in companies. Companies were working in technology for signal and image processing, but the problem is that in 2020, they received the Princesa de Asturias Award, the top 4 experts in the mathematical theory of image and signal processing, when actually they were experts in Fourier analysis. But of course, now in the Autonomous University of Madrid, you have to be an expert in Fourier transforms or you're out. But it was a huge surprise because everyone was completely convinced that that was the right approach. And there are some parts which I guess have more of a tailwind than others. And on the other hand, the idea that deep mathematics, what Jacobi said, are done in the honor of the human spirit, are difficult to see in terms of the direct impact. But they are an inherent part of our field, and I think all branches of mathematics need to follow their own road. But as Pilar said, we do need to all be connected and support one another. We're all mathematicians, and the effort we need to make so that the people in differential equations forget about Hilbert's 19th problem and start understanding Villama is a big push, and it takes a long time to get that knowledge transfer to happen, even in-house. It's a really big effort because people who are out there don't realize the effort it takes to keep this house united and connected and up to date. And I just wanted to add, continuing with what Diego was saying, that in fact, probably the reason why mathematicians are starting to be more respected socially is precisely because of the financial side of things, as Pilar was saying, because now companies are aware of the fact that by hiring mathematicians, they can raise their sales, their income, their profit, and reach more clients. And that's actually connected with a part which already came up in this discussion, which is AI and machine learning. Because ultimately, companies have realized that if you want to have good AI and good data analytics and good simulations and good modeling, you need to hire mathematicians. And so that's definitely something that is now very obvious in today's society, that mathematics can contribute a lot in AI. And perhaps this might have been one of the questions, but another interesting aspect could be what would happen in the opposite direction. Can businesses contribute something to mathematics? Can AI contribute something to mathematics? Is this just a one-way road or is it a two-way road? Just to give an example that comes to mind, Microsoft has created the Microsoft Research Station Q, where they've basically hired Fields medalists to create the next step beyond quantum computers. So he's basically brought them together and said, get on with it, do your mathematics. I don't care about the economic profit short term. Do your thing. So I was wondering whether those actors that are generally benefiting from mathematics might not also contribute something, and specifically whether AI could contribute something to mathematics today or not. Well, with that, which is really key issue. There's been so many ideas that it's going to be difficult to wrap it up. But we did want to open the floor for questions before we close.
Bueno, ha sido esto está siendo.
Oh, I am so thankful. I feel that this is a luxury, having these discussions. There's not a clear limit between physics, mathematics. You know, the chairperson is a physicist, there's a mathematician there, so we're all mixed here. Anyway, it comes to my mind that Einstein's study of the theory of relativity, general. He was competing with Hilbert, I believe, right? Am I right? In such a way that even Einstein lived the most anguished times of his life, it seems, right? Hilbert actually filed first or published the theory of relativity, but he modified it once it was published by Einstein's. So what calls my attention is the way a mathematician such as Hilbert can humiliate a physicist such as Einstein, so to say. I'm joking, but I'm serious. So from the mathematico-paritivistic point of view, what do you think about that? AI is another story. If you, David, are nervous, can you imagine how the rest of the ordinary people, plain people are? We're so nervous. I know that recently there was a week in London that ended up saying that it's a dangerous thing that we need to keep under control and so on. So, do you want my first approximation for an answer? The Einstein and Hilbert discussions, I don't know really much about, but I do know that in 2005 there was a 100th anniversary of Einstein, and I know because back then I studied that Einstein had an intuition because he was a physicist, and there's a deep thing. You need to see it before formalizing. You need to have the vision, and that is what explains El Satori talks about the Zen Buddhism visions. He saw it. He had a vision. But a well-trained mathematician, once he sees what he has to do, he can repeat the same solution several times. And there came a time when Hilbert learned from a lecture that unfortunately Einstein wanted to address in Göttingen before that he could several that theory that was almost ready in several nights. The problem of mathematicians is that once you give them the material, they know how to weave the basket. And that's a spectacular thing that physicians work better if they're together. Einstein, if he had not been advised about Minkowski's study or space, and I'm not an expert on this, but anyway, if he had not been advised to go that way, he would not have been able to prove his theory, right? You know what? Einstein was the person, nor Hilbert, nor any other, who realized that there could not be transmissions of information and signals at speed bigger than the light speed of light. That is the grounds for the theory of relativity, which is restricted. And as the Professor Vázquez has said, really that theory came out from a physicist because he knew that they needed to modify really the Newton's mechanic in order to solve certain anomalies that happened in the field of electrodynamics. So combining or mixing Hilbert, who was, by the way, an exceptional mathematician, with a person that had the intuition so that he could do 4 discoveries in 1 year, one of which would have been a Nobel Award. That unfortunately has not happened to a mathematician, but rather to a physicist. I don't know if anybody else wants to add something. 2 more questions.
Sí, a ver, A ver, ¿se me oye sin altavoz o no? ¿Se me oye?
Can you hear me even if I'm not using a microphone?
No.
Okay, then. Can you hear me better? Yes, please. I'm not going to talk about mathematics, not about neuroscience, not about physics, nor social impact. I'm just going to talk about my experience. I'm a civil engineer, and ever since I was 13, I was surprised myself at a formula of Euler that joined three transcendents, and it gave you a unit. And then I realized, oh my God, this is a synthetic analysis of reality. What I worry about is reality. I'm concerned about reality. And then I'm going to always ask the questions to all of my friends. And reality is that your mobile phone is ringing. Oh, really? Maybe I cannot hear it.
Jesus Christ.
Anyway, I'm going to continue with my reasoning. Mathematics are very important. I'm a business owner and I'm a civil engineer. And one of the final speakers I loved about how to relate all of the elements of mathematics. That's important. I always say that we should really wonder whether there's reality. Do we have a reality? If Alheim says reality doesn't exist, then I won't waste my time anymore. If that reality exists, can it be explainable? If they say no, then I don't go on. And then I wonder, I ask myself or my friends, do not believe that the best methodology is knowledge? Actually, mathematics is a branch of knowledge. Physics, neuroscience depend on the time we're living. And we can say no doubt that we are living great developments, but that's always happened in history. But all of us who are older, we believe that our time is more developed, but that's what explains life, change. So I have three concepts. I tell my friends, do you really believe that if there is a reality and if it can be explained, the best way for the explanation is the scientific method, and that's it? In my experience, I do use mathematics for my business, for my company. Yes, I do. And I believe that what we need to vindicate, to claim, is that what does this have to do with the amnesty law? Oh, yes, it does have to do.
What?
So, those of you who are thinking here, please, I do want to ask you to please transform what we need to transform, which is society. We need to transform our society. And the first question is, what type of society do we want? That's the first question, and then we will talk from then onwards. I'm delighted to listen to you, but that's one step ahead. We need to go more in general. As a citizen, I just wanted to leave it there.
Pues yo creo que nos estamos quedando sin tiempo.
We're running out of time. This type of reflections take us beyond the social impact, actually, yes. You're right. We're not philosophers, any of us. We had computer experts, physicists, engineers, mathematicians, many. But you know what? If we talk about reality and the way to interpret it, well, that would take us to another discipline, which is philosophy and almost theology, even. So, thank you to everyone. This is just, the time is over.
Lo único que quiero es...
I'd just like to thank all of the speakers, the two lecturers, especially the splendid lecturers that we've been heard, Yang Hui He, Pilar Bayer, the panelists. I'd like to thank the institutions for helping us organize this, and the audience, unfortunately, with time. Well, we've been losing them. But anyway, thank you very much to all of you.
Organizada organizadores, queríamos dar las gracias a los que quedáis. Sí que es verdad que, bueno, supervivientes de esta sesión bastante intensa. Han salido muchos temas.
Well, you've survived this intense session. There's been many messages that have been conveyed, but there's one that I'd like to convey related to social impact. We mathematicians are not just characters in a glass